In the deepest, coldest static of the cosmic microwave background, the afterglow of creation, a signal has been found that is mathematically impossible. It is a faint, structured echo that, by every measure, appears to originate from a time before the Big Bang. A fossil from a reality that existed before time itself. We have always believed that time began 13.8 billion years ago. But what if that wasn't a beginning, but a transition? What if our universe, our reality, is merely a crystal that grew from a timeless, information-rich abyss? Tonight, we journey to the absolute edge of existence before the first moment. We will examine the impossible, zero-point echo, explore a new theory of a timeless causal substratum, and confront evidence that suggests our universe is not a creation from nothing, but a phase change in an eternal, underlying reality. If you are ready to question the very nature of beginning and end, like and subscribe for this cosmic journey. Prepare yourselves, we begin. For decades, we believed we had found the edge of time, a wall beyond which our science could not see and our imagination could not travel. We called it the cosmic microwave background. It is the oldest light in the universe, an image of creation itself, released when the cosmos was just a newborn, a mere 380,000 years old. Before that moment, the universe was an impenetrable fog, a seething plasma of energy and elementary particles so hot and so dense that light was trapped, unable to travel more than an instant before being scattered. It was like trying to see through the heart of a star. The universe was opaque, a closed book. The cosmic microwave background, or CMB, is the light from the very moment that fog cleared, the instant the universe cooled enough for the first atoms to form, untrapping the light and allowing it to travel freely through space for the very first time. That ancient light has been traveling ever since, for 13.8 billion years, and it washes over us today as a faint, cold glow of microwaves, filling every direction of the sky. To our instruments, it is a near-perfect, uniform radiance, the thermal echo of the Big Bang. It became the bedrock of modern cosmology, our most profound confirmation that our universe did indeed begin in a hot, dense state. But it was also a boundary, a temporal horizon. It was our baby picture of the universe, and like any picture, it only shows a single moment. It told us nothing of the instant of birth itself, and it told us absolutely nothing of what might have come before. The question of a before was deemed meaningless, a philosophical dead end. It was like asking what is north of the North Pole. Time, we concluded, began with the Big Bang. There was no before on the map of reality. The CMB was the edge of that map. For generations of scientists, this was the final frontier of observation, a sacred wall we could approach, measure, and admire, but never, ever breach. But humanity has a habit of building instruments that see through walls. And in the pursuit of understanding our origins, we built a machine designed to listen to the faintest whispers from that primordial dawn. It was called the Planck Deep Field Array, a space observatory of unprecedented sensitivity, designed not to look for new signals, but to understand the absolute silence, the fundamental noise floor of reality itself. Its mission was to map the CMB with a precision so extreme it could detect the ghostly fingerprints of cosmic inflation, the theoretical hyperexpansion of the universe in its first trillionth of a second. It was an instrument built to hear the sound of creation itself. But it heard something else entirely. It heard an echo from a time that should not exist. The Planck Deep Field Array was a masterpiece of human engineering. Its detectors were cooled to within a fraction of a degree of absolute zero, making it one of the coldest places in the known universe. This extreme cold was necessary to reduce its own thermal noise, to allow it to hear the faintest possible signals from the dawn of time. It was the cosmic equivalent of building a soundproof chamber so perfect that you can hear the blood moving through your own veins. The array was designed to detect minute variations in the temperature and polarization of the CMB light. These variations we believed were the seeds of all cosmic structure. The quantum fluctuations from the Big Bang stretched to galactic scales by inflation. The mission was a resounding success. It mapped these fluctuations with breathtaking clarity, confirming the predictions of our standard cosmological model in exquisite detail. But as the scientists at the Max Planck Institute for Cosmology began the painstaking process of cleaning their data, of subtracting every known source of interference to isolate the pure, primordial signal, they found something that refused to disappear. It was a pattern, a faint, intricate, and impossibly large structure embedded within the very noise they were trying to eliminate. It was not a temperature fluctuation. It was not a gravitational wave signature. It was something else, a whisper so faint it was on the absolute threshold of detection, a pattern that seemed to be imprinted behind the CMB like a watermark on the fabric of reality itself. At first, they catalogued it as an instrumental artifact, a ghost, in the machine. No signal could be older than the CMB. It was a logical and physical impossibility. So they began the long, arduous process of elimination. They spent months, then years, checking every circuit, every line of code, every sensor on the probe. They cross-referenced their data with every other telescope on and off the planet. They built complex models of our own galaxy, mapping every wisp of interstellar dust, every flicker of synchrotron radiation, to ensure this signal was not simply a local contaminant, a smudge on the cosmic window. It was not. They modeled the effects of gravitational lensing, the subtle bending of light by trillions of galaxies and dark matter halos between us and the CMB. The signal did not match. It was not a distortion. It was a source. They considered the most exotic speculative theories within known physics. Could it be the decay of some unknown dark matter particle? Could it be the vibration of cosmic strings, theoretical defects in spacetime left over from the early universe? One by one, every explanation that began after the Big Bang failed. Each model they built, each simulation they ran, predicted a signal with different properties, a different shape, a different statistical signature. The anomaly remained stubbornly unique. It was a team led by a cosmologist named Dr. Aris Thorne that finally had to confront the impossible. Thorne was not a radical. He was a meticulous, respected scientist who had spent his life building the very standard model this signal now threatened to shatter. He was a cartographer of our cosmic origins, and he had found something that lay beyond the edge of his map. The signal, which his team had ironically nicknamed the 0-point echo, because they assumed it was a baseline instrumental error, had two properties that made it utterly alien. First, its scale. The pattern was coherent across the entire sky, on an angular size larger than the observable universe itself at the time the CMB was formed. This was a smoking gun. For a physical process to create such a large, connected pattern, information would have had to travel faster than the speed of light in the early universe, a flagrant violation of causality. Whatever created this pattern had to be outside the causal structure of our cosmos. It could not have originated from within. Second, and far more disturbing, was its mathematical signature. When the team analyzed the wave properties of the echo, they found it possessed what could only be described as negative temporal frequency. This is a concept so counterintuitive it borders on the nonsensical. It is like finding a sound wave whose vibrations are structured in a way that implies it traveled backward in time to its source. It was not just a signal that was ancient. The physics of the signal itself suggested it was pretemporal. It was a fossil not from an earlier time in our universe, but from a state of existence where our concept of time did not apply. The very idea was a heresy. It was a causal violation on a cosmic scale, akin to finding a detailed historical record of the Roman Empire, written in a language that would not be invented for another 1,000 years. It was an effect without a preceding cause within our reality. It was an echo of a sound that was never made in our universe. The implications were so profound, so existentially terrifying, that the team spent another 2 years in secret, desperately trying to find a flaw in their own work. They searched for a subtle miscalculation, a hidden bug in their analysis software, anything that could explain away the ghost in their data. They brought in outside experts, rival teams who would have been thrilled to find an error. None could be found. The signal was real, the analysis was correct, and physics, as we knew it, was broken. Dr. Thorne and his colleagues were left staring into an abyss. They had set out to take the sharpest possible photograph of the universe's beginning, and in doing so, they had found a crack in the photograph itself. Through that crack, they could hear a whisper from a place that should not be, a place before the first moment. After years of exhaustive, painstaking work, the moment of final reckoning arrived. In a quiet conference room, the data was projected for the last time. Every alternative had been exhausted. Every counter-argument had been refuted. There was only one conclusion left, a conclusion so heavy it seemed to draw the very light from the room. The signal was real, and it was not from here. It was the first piece of empirical evidence in human history that suggested our universe was not the beginning of everything. We were not looking at the moment of creation. We were looking at a shadow cast upon our reality, a shadow from a source that existed before time, before space, before the Big Bang itself. The wall at the end of the universe was not a wall, it was a window, and something was looking back. To truly grasp the magnitude of that discovery, to feel the very ground of reality breaking beneath our feet, we must first walk the solid earth of what we thought we knew for certain. Before the whisper from nowhere, there was the triumphant roar of a century of science. Before the crack in the cosmic egg, there was the story of the egg itself. A story so powerful, so elegant, and so complete that we believed we had finally read the first and final chapter of existence. To understand the heresy of the zero-point echo, we must return to the bedrock of modern cosmology. We must go back to the established reality. For nearly 100 years, our understanding of everything has been anchored in a single, powerful narrative, the story of the Big Bang. It begins 13.8 billion years ago, at a moment we label time zero. Before this moment, there is nothing in our equations, no space, no time, no matter, no laws. Then, from a single point, a singularity, of infinite density and infinite temperature, a concept so extreme it is less a place and more a breakdown of physics itself, everything erupted, all the matter that would one day form you, and me, and the earth beneath us, all the energy that would ignite a trillion stars, all of space, and crucially, all of time, exploded into being. This was not an explosion in space, like a bomb detonating in an empty room. That is the single most common and most profound misconception. There was no pre-existing room, there was no void. The Big Bang was the explosion of space. It did not expand into anything because it was the creation of the very concept of inter. It was the birth of distance, the invention of direction, the beginning of here and there. In that first, unknowable instant, the universe was its own container, and it was creating that container as it grew. The most powerful analogy we have, though imperfect, is that of an expanding balloon. Imagine you are not an observer watching the balloon inflate from the outside. Instead, imagine you are a two-dimensional being living on the surface of the balloon itself. Your entire universe is the rubber surface. On this surface you have painted countless dots, each representing a galaxy. As someone blows air into the balloon, the rubber stretches. From the perspective of any single dot, all the other dots are moving away. and the farther away a dot is, the faster it appears to recede because there is more stretching rubber between you and it. This is the crucial insight. The dots are not sliding across the surface. The surface itself is expanding, carrying the dots along with it. In this model, there is no center to the expansion on the surface. Every dot can claim to be the center, because from every dot, the view is the same. And most importantly, the question, what is the balloon expanding into, is unanswerable from within your two-dimensional universe. The air, the room, the person blowing into it, these all exist in a third dimension you cannot perceive or interact with. For you, on the surface, the universe simply gets bigger. It creates more of itself, more surface everywhere, all at once. Our universe, according to the standard model, is like that balloon surface, but in 3 dimensions. And so, for a century, we taught ourselves that the question, what was there before the Big Bang, was a failure of the imagination, a logical fallacy, a question that had no answer because it was improperly formed. It was, as the great physicists would say, like asking what is north of the North Pole. Once you are at the pole, at the absolute origin point, the concept of north ceases to have meaning. The Big Bang, our TW0, was the North Pole of time. There was no before on the map of reality because the map itself began there. The singularity was the absolute beginning, the ultimate edge beyond which our inquiries could not and should not go. This model was not a guess. It was not a matter of faith. It was a scientific theory built upon 3 colossal pillars of observational evidence, each one a monumental discovery in its own right, each one confirming the others in a symphony of cosmic truth. The first pillar was the one discovered by Edwin Hubble in the 1920s. Using the most powerful telescope of his time, he patiently measured the light from distant galaxies, then called spiral nebulae. He discovered that the light from almost every single one of them was stretched, its wavelength shifted toward the red end of the spectrum. This is the cosmic equivalent of the Doppler effect, the way the pitch of an ambulance siren lowers as it speeds away from you. This redshift meant the galaxies were receding, but the truly revolutionary discovery was the pattern. The farther away a galaxy was, the faster it was moving away from us. This was not a random scattering of objects from a central explosion. This was the signature of the metric of space itself expanding everywhere. It was the first empirical proof that our universe was not a static, eternal stage, but a dynamic, evolving entity. It was the observation that first breathed life into the idea of a cosmic beginning. The second pillar was discovered by accident in the hiss of static from a radio antenna in New Jersey in 1965. 2 physicists, Arno Penzias and Robert Wilson, were trying to eliminate a persistent, faint background noise that contaminated their measurements, no matter where they pointed their instrument. They cleaned it, recalibrated it, even chased away pigeons they thought might be the source. The noise remained. What they had found was the theory's most dramatic and specific prediction come to life. They had found the afterglow of the Big Bang, the cosmic microwave background. If the universe had begun in an incredibly hot, dense state, then it must have been filled with intense radiation, a brilliant light. As the universe expanded and cooled, that light would have cooled with it, its wavelength stretching from visible light into the microwave spectrum. The theory predicted that this primordial glow should still be detectable today, as a cold, uniform bath of radiation filling all of space, and that is precisely what Penzias and Wilson had found. It was the echo of creation, cooled to just under 3 degrees above absolute zero, still washing over the cosmos 13.8 billion years after it was released. It was the smoking gun, the definitive proof that our universe had indeed been born in fire. The third and final pillar was written in the very atoms that make up our world. The Big Bang model made another set of precise, falsifiable predictions. In the first few minutes after time zero, the entire universe was a nuclear furnace, hotter and denser than the core of our sun. In this crucible, the first atomic nuclei were forged in a process called Big Bang nucleosynthesis. The theory predicted the exact ratios of the light elements that should have been cooked in this primordial soup. It calculated that the early universe should have produced a cosmos made of roughly 75% hydrogen, 24% helium, and trace amounts of lithium and other light elements. This was a staggeringly bold prediction. And when astronomers pointed their telescopes to the oldest, most pristine clouds of gas in the universe, to the atmospheres of the most ancient stars, they found those exact ratios confirmed to stunning precision. The universe's chemical composition was a fossil record of its first 3 minutes. Together, these three pillars, the expansion of the universe, the existence of the cosmic afterglow, and the primordial abundances of elements, formed an unshakable foundation. They told a single, coherent story. Our universe began in an infinitely dense singularity. It expanded and cooled. In the first few minutes, it forged the elements. For 380,000 years, it was an opaque plasma. Then it cooled enough to become transparent, releasing the light we see today as the CMB. And for the next 13.8 billion years, gravity pulled the cooling matter together into the galaxies, stars, and planets we see today. The laws of physics themselves were born in this furnace. The arrow of time, the inexorable march from past to future, was set by the universe's expansion from a simple, ordered state to a complex, disordered one. This was the established reality, a complete and self-contained story of cosmic origins. The book of the cosmos had been written, and its first page was the singularity. There was no page zero. And for a time, this story was enough. It was more than enough. It was a triumph of the human intellect, a cosmic creation myth grounded in mathematics and observation. The book of the universe was closed at its beginning, but then a faint, impossible whisper was heard in the silence, and the first page of that book was violently torn out. Aye. The zero-point echo shattered this tidy picture. It took the perfect, complete story of our origins and introduced a character who should not exist, a presence from a place that has no name in our physics. When Dr. Thorne's team finally accepted that the signal was real, they began the terrifying work of characterizing it, of trying to understand the physics of a fossil from a non-existent time. And the first property they confirmed was the one that broke the laws of causality most flagrantly. The echo possessed what they were forced to call, for lack of a better term, negative temporal frequency. To understand this concept, you must first picture a normal wave, like a ripple on a pond. The frequency of the wave is simply how often its crests pass a certain point. It is a measure of oscillation in time. A high frequency means many crests per second, a low frequency means few. Every signal we have ever measured, from the light of a distant star to the sound of a human voice, has a positive frequency. Its oscillations move forward through time, from cause to effect. It is the most fundamental rhythm of our reality. The zero-point echo did not follow this rhythm. When analyzed mathematically, its wave components were inverted. They were structured as if they were propagating not from the past into the future, but from a direction orthogonal to time itself. It was a signal whose internal clock was not ticking forward. It was not ticking at all. The very mathematics used to describe its shape implied a source that did not participate in our universe's timeline. It was not just old, it was pre-temporal. Think of it this way. Imagine archaeologists unearth a perfectly preserved fossil. Standard dating techniques reveal the rock layer it was found in is 100 million years old. But upon examining the fossil itself, they find it contains biological structures and genetic material that could only have evolved 100 million years in the future. That is a paradox. Now, imagine something even more impossible. Imagine they analyze the atomic structure of the fossil and find that its atoms are arranged in a way that suggests they experienced a negative amount of time. The very concept is incoherent. It is not a fossil from the past or the future. It is a fossil from a time that is mathematically impossible. The zero-point echo is that impossible fossil. Its existence is not just an anomaly, it is a contradiction in the very language of physics. It is an effect whose cause cannot be located anywhere on the timeline of our universe, not even at the moment of the Big Bang itself. It points to a source that lies outside of time as we know it. The second property that confirmed the echo's alien origin was its sheer, impossible scale. When we look at the cosmic microwave background, we are looking at a snapshot of the universe when it was a mere infant, 380,000 years old. At that time, the entire observable universe of today was compressed into a region of space so small that light had not yet had time to cross it. The cosmic speed limit, the speed of light, created a strict boundary on how large any coherent connected structure could be. This is called the cosmic horizon. Think of it like a ripple expanding from a stone dropped in a pond. The ripple can only travel so far in a given amount of time. In the early universe, no physical effect, no heat, no information, no causal influence of any kind could have traveled faster than light to coordinate conditions across vast distances. This is why the near-perfect uniformity of the CMB was such a mystery before the theory of cosmic inflation. Inflation solved this problem by suggesting the entire observable universe was once a microscopic patch that was in causal contact before being stretched to an enormous size, but the zero-point echo violated even this inflationary solution. The structure of the echo, the intricate pattern of its polarization, was coherent across angular scales on the sky that were vastly larger than the cosmic horizon at the time the CMB was released. It was a single, connected pattern that spanned regions of the early universe that could not have possibly communicated with each other. It was like finding two ancient sealed tombs on opposite sides of the earth, each containing a manuscript written by a different person, yet they are both identical, word for word, down to the tiniest pen stroke. There is no natural explanation, no signal could have traveled between them to coordinate the writing. The only conclusion is that the information, the blueprint for the manuscript, must have come from a common source that existed before the tombs were sealed, a source that was external to both. The zero-point echo was that identical manuscript written across causally disconnected regions of our early universe. This proved with near absolute certainty that whatever created the echo was not a process that happened within our spacetime after the Big Bang. It had to be an external influence, an imprint from a deeper, larger, and older reality that set the initial conditions for our own. The echo was not a feature of our universe's birth. It was a feature inherited at birth. The scientific community's reaction was, predictably, one of profound skepticism. This is not a weakness of science, it is its greatest strength. Extraordinary claims require extraordinary evidence, and a signal from before time is the most extraordinary claim one could possibly make. The publication of Thorne's paper set off a firestorm of debate. It was a direct assault on the most fundamental tenet of modern cosmology. For decades, the community had pushed back against any notion of a before, dismissing it as the realm of mystics and philosophers, not physicists. Now, here was data, cold, hard numbers from their most trusted instrument, suggesting the philosophers might have been onto something. The first wave of reaction was to find a mundane explanation, to prove that this was all a grand mistake. Dozens of competing teams around the world began to develop alternative models. They were not trying to prove Thorne right, they were trying to prove him wrong, to save the standard model from this impossible contradiction. The most plausible conventional explanation was that the signal was not primordial at all, but a complex foreground effect created by something between us and the CMB. perhaps it was an undiscovered population of interstellar dust in our own galaxy. Dust grains, especially if they are aligned by magnetic fields, can polarize light. If there existed a vast, previously unmapped network of these grains stretching across the entire sky, it could theoretically mimic some aspects of the echo's pattern. Another leading idea involved primordial magnetic fields. Some theories suggest that the early universe was threaded with incredibly powerful magnetic fields. As the plasma of the early universe swirled within these fields, it could have generated complex polarization patterns in the light that would eventually become the CMB. This was a compelling idea because it used known physics, electromagnetism, to explain the anomaly, without needing to invent anything new or pretemporal. A third, more exotic but still conventional, theory pointed to a network of cosmic strings. These are theoretical defects in the fabric of space-time, one-dimensional cracks left over from phase transitions in the very early universe. A vast network of these strings crisscrossing the cosmos could gravitationally lens the CMB light, twisting its polarization in complex ways. If the network had a specific, previously unconsidered geometry, it might be able to reproduce the large-scale coherence of the echo. For several years, these alternative theories dominated the conversation. Each one represented a plausible, if complex, way to explain the data without resorting to the radical notion of a pre-Big Bang reality. The scientific process was working as it should. The anomaly had been found, and now the community was rigorously testing every possible explanation within the bounds of known physics. Thorne and his team welcomed the scrutiny. They knew their claim would, and should, face the highest possible standard of proof. But as they and others tested these alternative models against the high-precision data from the Planck array, a new and deeper sense of unease began to settle in. The mundane explanations were not working. Each attempt to explain the zero-point echo with physics from after the Big Bang failed, but they failed in illuminating ways. The process was like trying to fit the wrong key into a complex lock. The key might fit part of the way, it might even turn a little, but it could never open the mechanism. Each failure taught the scientists more about the true shape of the lock. The interstellar dust model collapsed first. While dust can create polarization, the frequency spectrum of that polarization is predictable. Dust emits and polarizes light differently at different frequencies. When astronomers looked at the echo using data from multiple frequency bands, from radio waves to infrared, they found the signal's strength and structure remained almost perfectly constant. Real dust would have looked different at different frequencies. The echo did not. It was spectrally flat, a behavior that no known type of dust could produce. The model was ruled out. The primordial magnetic field hypothesis proved more resilient, but it too eventually fell. While powerful magnetic fields could twist the light of the CMB, they would also leave other, more obvious fingerprints. They would create specific types of non-Gaussian patterns in the temperature fluctuations of the CMB, subtle statistical correlations that the Planck data was perfectly designed to find. Scientists performed the analysis, searching for these telltale magnetic signatures correlated with the echo's location. They found nothing. The universe, at the time the CMB was released, appeared to be remarkably free of large-scale magnetic fields. The cause of the echo was magnetically silent. The cosmic string network theory was the last and most speculative conventional hope, but it suffered from a fundamental problem of scale. To create a coherent pattern as large as the zero-point echo, the string network would have to be incredibly uniform and possess a bizarre, almost artificial geometry. More importantly, such a network would produce sharp, linear discontinuities in the CMB where the strings themselves passed. High-resolution searches for these cosmic string wakes came up empty. The CMB was smooth, with no evidence of the sharp creases a string network would create. One by one, the lifeboats of conventional physics were sinking. The process took years of intense, often contentious debate. Every new analysis that ruled out an alternative theory deepened the mystery. the anomaly was being cornered. With each failure to explain it, the signal's strange properties became sharper and more undeniable. It was not dust, it was not magnetism, it was not cosmic strings. The feeling in the cosmological community shifted from skepticism to a growing sense of dread and excitement. They were facing a true unknown. The data was unambiguous. The signal was real, and it did not conform to any physical process that could have occurred within the history of our universe. The community was left in a state of profound cognitive dissonance. The pillars of the Big Bang model were still standing, solid and immovable. But now, leaning against them, was an impossible artifact, a fossil from a time that the model itself said could not exist. Physics had pushed its narrative to the very first moment of time, and in doing so, had found a footprint left on the shore from a visitor who arrived before the ocean was even formed. The scientific community, stripped of all conventional explanations, was finally forced to admit the unthinkable. They had no explanation. The zero-point echo was a true anomaly, a verified observation of our universe that stood in stark violation of our most cherished physical laws. The Book of the Cosmos did not begin on page 1. And for the first time, we had the proof. This is the moment in every great detective story where the pieces of an impossible crime lie scattered on the floor. The doors were locked from the inside. The timeline makes no sense. The clues contradict each other. All conventional suspects have been eliminated. The investigators are left with nothing but the certainty that something has happened which their rulebook says is impossible. This is the state in which cosmology found itself. The zero-point echo was the impossible crime, and the laws of physics were the rulebook it had broken. With every conventional explanation exhausted, the field fell into a period of quiet crisis. The data was undeniable, but the implications were unthinkable. To move forward, someone would have to be willing to tear up the rulebook entirely. Someone would have to be brave enough, or perhaps desperate enough, to propose an explanation that was not just new, but fundamentally alien to our entire conception of reality. That task fell to Dr. Aris Thorne and his team. For them, this was not an abstract puzzle, it was a personal crisis. They had found the anomaly. They had weathered the storm of skepticism. They had meticulously dismantled every attempt to explain it away. And now they were left alone with their impossible discovery, staring into the abyss they had opened. Their whiteboards, once filled with the elegant equations of standard cosmology, were now covered in question marks and paradoxes. They were trying to find the source of a signal that came from a time before time, a place before space. How do you even begin to write an equation for that? Their search for a solution was not a single eureka moment, but a slow, agonizing descent into the strange landscapes of theoretical physics, far beyond the comfortable shores of observation. They explored ideas that had long been confined to the fringes of science, speculations about the nature of information, the meaning of causality, and the fundamental structure of reality itself. They were no longer just doing cosmology, they were venturing into metaphysics, but with the ruthless discipline of mathematics as their only guide. They were looking for a new story, a new creation myth that could somehow contain their impossible fact without breaking the rest of physics. And then, after years of working in this intellectual wilderness, they emerged with a proposal. A hypothesis so radical, so profound, it made the Big Bang itself seem like a minor detail in a much grander and far stranger story. It was a theory that did not just add a new chapter before page 1, but suggested that the Book of the Cosmos was written in a language we had never even imagined. They called it then this Causal Substratum hypothesis, and it begins with a simple, terrifying premise. Before the Big Bang, there was no time, but there was nothing. The hypothesis posits that underlying our entire reality, deeper than space, deeper than time, deeper than quantum fields, there exists a fundamental layer of existence. This is the causal substratum. It is not a physical place, It is a timeless, spaceless ocean of pure information. It is a realm of pure causal potential, a substrate where the relationships that would one day become our laws of physics exist as a network of pure logic. Think of it not as an empty void waiting to be filled, but as a supersaturated solution, a liquid potential containing the blueprints for every possible universe, every conceivable set of physical laws, all coexisting in a state of perfect, timeless equilibrium. In this substratum, there is no before and after. There is only causes and is caused by. The arrow of time is not a feature of this realm. It is a reality built on pure atemporal causality, like the axioms of mathematics. The Pythagorean theorem is not true on a Tuesday. It simply is. The causal substratum is the ultimate mathematical truth, a realm where all possible realities exist as latent, informational patterns, each one a perfect, self-consistent set of rules waiting for an opportunity to manifest. Our universe, with its specific laws, the speed of light, the strength of gravity, the charge of an electron, is just one of those infinite patterns, one possible song encoded in the silence. According to this hypothesis, our universe did not begin with a bang from a singularity. It came into being through a process far more familiar to us, a process we see every day in the world around us. It began with a phase transition. Think of a glass of perfectly pure, supercooled water. It is still liquid, even though it is below its freezing point. It is in a state of unstable potential, a liquid chaos. It remains in this state until something triggers a change, a single speck of dust, a tiny vibration, and then, in a flash, the entire glass freezes. A cascade of crystallization spreads outwards from that single point, and the chaotic, formless liquid locks into a rigid, ordered, crystalline structure. In that moment of freezing, everything changes. The properties of the water are transformed. The liquid's freedom of movement is replaced by the ice's fixed lattice. New rules, new properties emerge that were not present in the liquid state. The causal substratum hypothesis proposes that the Big Bang was a phase transition on a cosmic scale. The timeless, formless ocean of the substratum was that supercooled liquid. A random quantum fluctuation, a single informational vibration, was the speck of dust. That fluctuation triggered a cascading crystallization event. A set of informational rules, the specific pattern that would become our physical laws, suddenly locked into a stable, self-propagating structure. That structure, that magnificent, four-dimensional crystal, is our space-time. The Big Bang was not an explosion, it was the moment of freezing. The moment when timeless, infinite potential collapsed into a concrete, actualized reality. And in that moment of crystallization, a new property emerged that did not exist in the liquid substratum, a property that would come to define our entire experience of reality, time. The arrow of time, the linear progression from past to present to future, is an emergent feature of the crystal. It is the rigid structure of the lattice, the fixed causal chain of cause and effect that propagates forward through the frozen reality. In the timeless liquid of the substratum, all causal connections existed simultaneously. In the frozen crystal of space-time, those connections are forced into a sequence. That sequence is what we feel as the flow of time. This hypothesis is staggering in its elegance, because it instantly transforms the zero-point echo from an impossible anomaly into a necessary prediction. If our universe was born in a cataclysmic freezing of reality, then that process could not have been perfectly silent. A phase transition of this magnitude, the crystallization of an entire reality from a timeless potential, would have sent violent shockwaves through the substratum. It would have been the single most energetic event in all of existence. The sound of space-time freezing, the informational ripple from that crystallization front, would have been imprinted on the very fabric of our universe at the moment of its birth. It would be a fossil of the transition, a permanent scar. The zero-point echo Thorne's team proposed is that fossilized sound. It is the vibration from the moment of freezing, permanently imprinted on the oldest light in our universe. Its strange, pretemporal properties are the signature of its origin. It sounds alien to us because it is a sound from a realm without time. Its impossibly large scale is explained because it was not created by a process within our spacetime, but by the very process that created spacetime. It is the shadow of our own creation. This new model reframes the entire question of our cosmic origins. The Big Bang is no longer a creation from absolute nothingness, the ultimate metaphysical mystery. In science, creation from nothing, ex nihilo, has always been a point of discomfort, a moment where physics seems to give way to magic. But in the causal substratum model, there is no creation from nothing. There is a transition from something, from one state of reality to another, from a timeless, potential state to a temporal, actual state. It replaces a philosophical paradox with a physical process. A phase transition is something we can understand, model, and test. And this provides the hypothesis with its most crucial feature. It is science, not philosophy, because it is falsifiable. The theory makes a clear and brutal prediction. The zero-point echo must be a relic of this pre-temporal phase transition. If, at any point in the future, any other explanation is found, if the echo is ever proven to be a local effect, a complex lensing pattern, or any other phenomenon that occurs after time zero, then the causal substratum hypothesis is wrong. The entire edifice collapses. It is a theory that lives or dies on the authenticity of this single ghostly signal. The power of the hypothesis lies in its terrifying but logical elegance. It suggests that our entire universe, every galaxy, every star, every atom, every thought you have ever had, is merely one possible pattern, one frozen crystal in an infinite, timeless sea of potential. Our reality, with its immutable laws and its forward-marching time, is a special, emergent case. We are living within a structure, and the structure itself is a product of a deeper, more fundamental reality. This is a profound shift in perspective. It dethrones our universe from being the entirety of existence to being a single instance of it. But it also offers a solution to one of the deepest mysteries of all. Why is our universe so perfectly suited for existence? Why are the fundamental constants of nature so exquisitely fine-tuned to allow for complexity, for stars, for life? The standard model has no answer. It simply accepts these values as given. But in the causal substratum model, there is a potential answer. If the substratum contains the blueprints for all possible universes, then perhaps only certain types of crystals, certain sets of laws, are stable. Perhaps countless other universes have tried to crystallize from the substratum, but their internal rules were inconsistent, and they immediately melted back into potential. Our universe may simply be one of the patterns that worked. We exist because our laws form a stable, self-consistent structure. Our reality is not a miracle. It is a survivor. We are left with an image of existence that is both humbling and awe-inspiring. A timeless ocean of pure potential, and within it, a single, magnificent crystal. A crystal we call home. But for this beautiful idea to be more than just a story, it would need more evidence than a single, ghostly echo from the dawn of time. It would need corroboration from other fields of science, from independent lines of inquiry. And as cosmologists began to seriously consider this radical new picture of reality, they found that other scientists in other fields had already found their own impossible footprints on the shores of time. The greatest scientific breakthroughs are rarely a single, isolated flash of insight. They are a slow dawn, a gradual convergence of light from different corners of the sky, each beam illuminating the same, previously hidden landscape. A radical idea born in one field remains an orphan, a curiosity, until it is recognized by a sibling in another. While cosmologists like Aris Thorne were grappling with the ghost in their data, a signal from the edge of time, they were unaware that other scientists, working in realms unimaginably different from their own, were finding their own ghosts. They were finding cracks in the foundation of reality at the smallest possible scales, and bubbles of impossible physics at the largest. These were not, at first, seen as connected. They were separate, isolated mysteries, thorns in the side of their respective fields, but they were all pointing in the same direction. They were all pointing to a world beneath our own. The journey to the first piece of corroborating evidence takes us from the edge of the observable universe to the heart of matter itself. It takes us to a place beneath the mountains of the Swiss-French border, to the Large Hadron Collider at CERN. This is the most complex machine ever built by humanity, a 27-kilometer ring of superconducting magnets and particle detectors, a cathedral of science designed for a single, violent purpose: to smash protons together at nearly the speed of light. The goal of this magnificent violence is to recreate, for a fleeting, infinitesimal moment, the conditions of the Big Bang. In the fire of these collisions, for a trillionth of a second, the fundamental particles and forces that govern our universe are laid bare. It is an act of cosmic archaeology, digging through the layers of reality to glimpse the building blocks of existence. For years, the LHC had been confirming the predictions of the Standard Model of particle physics with breathtaking precision. It found the Higgs boson, the final missing piece of that theoretical puzzle. It measured the properties of quarks and gluons with an accuracy that seemed to leave no room for new physics. The machine was, in a sense, a victim of its own success. It was confirming what we already knew, but it had not yet found a signpost to the unknown lands beyond our current understanding, until it did. The anomaly appeared not in a shower of exotic new particles, but in a subtle, almost trivial detail of timing. When protons collide at such immense energies, they shatter into a spray of other, short-lived particles. The Standard Model is a rulebook that predicts, with mathematical certainty, the sequence of these events. First, the protons collide. Their constituent quarks and gluons interact. New, unstable particles are formed. Then, after a specific predictable delay, these unstable particles decay into more stable forms, like electrons, neutrinos, and their heavier cousins, muons. The sequence is absolute. Cause must precede effect. A particle must be fully formed before it can begin to decay. The timeline for these processes is measured in attoseconds, a billionth of a second. But our detectors are fast enough to resolve this sequence. They are the ultimate high-speed cameras, capable of watching reality unfold frame by infinitesimal frame. And in that footage, they saw something impossible. A new class of muons began to appear in the debris of the most energetic collisions, but they were appearing too soon. The detectors registered their decay products fractions of a nanosecond before. The complex chain of quark interactions that was supposed to create them could have possibly completed, according to the Standard Model. It was like watching the smoke from a fired gun appear before the trigger was pulled. It was like seeing the fragments of a shattered vase land on the floor before the vase had even fallen off the shelf. It was a microscopic but blatant violation of causality. The physicists at CERN did what all good scientists do. They assumed it was an error in their own equipment. They spent years recalibrating their detectors, checking the fiber optic cables that carried the timing signals, searching for a subtle electronic delay that could explain the illusion. They ran countless control experiments. They cross-checked their results between the two massive independent detectors, Atlas and CMS. The anomaly persisted. The muons were undeniably arriving ahead of schedule. They were reluctantly given a name that captured the horror of their existence: a causal muons. Within the framework of known physics, these particles could not exist. They were a paradox made manifest. But when the news of this anomaly reached the cosmologists studying the zero-point echo, it was not seen as a paradox. It was seen as the first echo of their own discovery, a whisper from the quantum realm that mirrored the one they had found at the cosmic scale. The causal substratum hypothesis offered a stunningly direct and elegant explanation. In the phase transition model of the Big Bang, our spacetime is a crystal that froze out of the timeless substratum. The laws of our universe, including the strict precession of cause and effect, are the properties of this crystal. But what if the crystal isn't perfect? What if under extreme stress it could be momentarily cracked? The proton collisions at the LHC are the most energetic events humanity can create, the closest we can come to the energies of the Big Bang. The hypothesis proposed that in the heart of these collisions, for an instant, the energy density becomes so high that it creates a microscopic fracture in the fabric of space-time. A tiny, fleeting tunnel that connects our reality to the timeless substratum beneath. The particles created in this inferno do not just exist in our space-time. For a fraction of a moment, their quantum wave functions can leak or tunnel through this crack, gaining access to the underlying ocean of pure causality. In the substratum, there is no linear time. There is no before and after. All causal pathways are accessible simultaneously. A particle tunneling through this realm is not bound by our rigid, one-way street of time. It can take a shortcut. It can access a causal pathway that is simply not available within the space-time crystal. From our perspective, trapped within the flow of time, this looks like a violation of causality. The muon's decay seems to happen before its creation is complete, because part of its process has taken a path outside of time itself. It is not time travel, it is something far more profound. It is accessing a reality where time doesn't flow. The anomaly of the acausal muons was transformed. It was no longer a violation of physics. It was the first experimental confirmation that a deeper, non-temporal layer of reality exists, and that under the right conditions we can touch it. The hypothesis explained not just the existence of these muons, but a detail that had baffled the CERN physicists. They only appeared in the most violent, highest energy collisions. This was exactly what the model predicted. Only the most energetic events could crack the space-time crystal and open a temporary gateway to the substratum. It was a perfect fit. The first piece of corroborating evidence had arrived, not from a telescope pointed at the heavens, but from a particle accelerator pointed at the heart of matter. The second line of evidence came from the opposite end of the scale. It came not from the infinitesimally small, but from the unimaginably large. It came from the great, empty deserts of the cosmos. For decades, astronomers had been mapping the large-scale structure of the universe, the cosmic web of galaxies and dark matter. They found that galaxies are not distributed randomly. They are arranged in a vast, foam-like structure, forming immense filaments and walls that surround enormous, almost empty regions called cosmic voids. These voids are the largest structures in the universe. The Boates void, one of the most famous, is a bubble of near-total emptiness nearly 330 million light-years across. If our own Milky Way galaxy were at its center, we would not have even known other galaxies existed until the 1960s. They are cosmic oceans of nothingness, regions that lost the gravitational lottery in the early universe, and from which matter has been flowing away for billions of years. According to the standard cosmological model, these voids should be relatively simple places. As the universe expands, driven by the mysterious force of dark energy, the voids should expand along with it. Just like everything else, their expansion should be passive, a simple consequence of the global stretching of spacetime. But as our maps of the cosmos became more precise, astronomers noticed something strange. The voids were expanding faster than they should be. The space inside these empty regions was stretching at a rate that could not be explained by the known value of dark energy alone. It was as if the voids were not just passively being carried along by the cosmic expansion, but were actively pushing outwards, inflating like overpressurized bubbles in the cosmic foam. This anomalous expansion was a subtle effect, but a persistent one, seen in multiple voids across the sky. It was another crack in the standard model. Dark energy, whatever it is thought to be a property of space itself, a cosmological constant that should be the same everywhere. Why would it be stronger, more repulsive, inside these empty regions? The causal substratum hypothesis offered another startlingly direct answer. Let us return to the analogy of space-time as a crystal freezing from a liquid ocean. A real-world crystal is never perfect. As it freezes, it often traps small pockets of liquid within its structure. These are known as inclusions. They are imperfections in the crystalline lattice, regions where the phase transition was incomplete. The hypothesis proposed that the great cosmic voids are the cosmic equivalent of these inclusions. They are not just empty space. They are vast, unfrozen, or incompletely crystallized remnants of the original causal substratum trapped within the crystal of our space-time. If this were true, it would explain their anomalous expansion perfectly. The substratum is a more fundamental, more energetic state of reality than our space-time. A trapped bubble of this pre-temporal liquid would exert a powerful outward pressure on the surrounding crystal. It would behave like a pocket of high-pressure gas trapped in ice, pushing the ice apart from within. This is not dark energy. It is a new physical mechanism, a repulsive force generated by the ontological difference between the timeless substratum and our temporal space-time. The voids are expanding faster because they are not empty. They are full of a different kind of reality, a reality that is pushing our universe apart from the inside. This was a breathtaking revelation. It connected the largest, emptiest structures in the modern universe to the very moment of its creation. The voids were no longer just passive voids. They were active, dynamic relics of the pre-Big Bang state. They were our only windows into the uncrystallized ocean of potential from which our reality emerged. And so the pieces began to lock into place. Three great mysteries from three utterly disconnected fields of science had appeared independently. In cosmology, an impossible echo from before the Big Bang. In particle physics, a particle that seemed to violate the arrow of time. In astrophysics, vast voids that were expanding too fast. On their own, each was a baffling, isolated anomaly. But when viewed through the lens of the causal substratum hypothesis, they were no longer anomalies. They were a triad of predictions. They were three sides of the same, terrifying new truth. The echo was the sound of reality freezing. The muons were cracks in the crystal. The voids were the bubbles trapped within it. It was a stunning convergence, a consilience of evidence that spanned the entire history and scale of the cosmos, from the smallest possible particles to the largest possible structures. The story of a universe born from a timeless ocean was no longer just a wild speculation. It was a scientific theory with multiple, independent lines of observational support. The case was building. The ground of reality was shifting. And the next layer of evidence would come from even more unexpected corners of the cosmos, tightening the net and leaving the old story of our origins with nowhere left to hide. A theory supported by a few strange coincidences is a curiosity. A theory supported by multiple independent lines of evidence becomes a contender. But for a theory to become a paradigm, to overturn a century of established science, it requires more. It requires a deeper convergence, a level of proof so precise and so interconnected that it transforms coincidence into certainty. The initial clues were powerful, but they were also low resolution, like a blurry photograph of a new continent. To bring that continent into sharp focus, to map its coastlines and understand its features, science required better instruments, more data, and a willingness to look even closer at the anomalies that were tearing the old maps apart. The scientific community, now galvanized by the possibility of a new cosmology, began to build those instruments. The first target was the zero-point echo itself. The original detection by the Planck Deep Field Array was revolutionary, but it was at the very limit of that instrument's sensitivity. It was a faint whisper in a storm of cosmic noise. To truly understand its structure, to confirm its alien properties beyond any shadow of a doubt, a new observatory was needed. It was built in the most remote and radio-quiet place on Earth, the high plateau of Antarctica. It was called the South Pole Temporal Array. It was not a single telescope, but a network of hundreds of highly sensitive detectors spread over miles of ice, all linked together to function as a single, continent-sized instrument. Its sole purpose was to stare, uninterrupted, at the sector of the sky where the zero-point echo was strongest, and to listen, with a sensitivity 100 times greater than Planck, to the sound of a reality freezing. After 3 years of continuous observation, shielded from earthly interference by 2 miles of solid ice below and the thin, clean Antarctic air above, the temporal array delivered its verdict. The zero-point echo was not only real, it was more complex and more structured than anyone had imagined. And that's fine. The new, high-resolution data confirmed its pre-temporal nature, its impossible scale, and its complete lack of correlation with any known astrophysical foregrounds. With a statistical significance that now exceeded 9 sigma, a level of certainty in physics that is considered indisputable discovery, the alternative models were not just disproven, they were annihilated. The data was so clean that with a 99.9% confidence level, the signal was confirmed to have no connection to interstellar dust, primordial magnetic fields, or cosmic strings. But the new data revealed something even more profound. The echo was not a smooth, uniform signal. When the team zoomed in on the data, they found that the polarization pattern possessed an intricate, self-repeating structure. It was a fractal, a mathematical object that displays the same pattern at every level of magnification. Think of a snowflake, where each of its 6 arms is a smaller version of the whole, and each branch on those arms is a smaller version still. The zero-point echo had this same property, a nested hierarchy of structure that extended down to the smallest scales the temporal array could resolve. This was the smoking gun that connected the echo directly to the physics of a phase transition. When a liquid crystallizes, the process is rarely smooth. It is a chaotic, branching event. Ice crystals spread out in fractal patterns, forming intricate dendrites that branch and sub-branch as the freezing front advances. The mathematics that describe this process, the physics of cascading failures and emergent order, predicts precisely this kind of fractal structure. The team ran simulations, modeling the Big Bang as a crystallization event within a hypothetical substratum. The shock waves produced in these simulations, the theoretical sound of freezing, created polarization patterns in the CMB that matched the fractal details of the zero-point echo with breathtaking fidelity. It was no longer just a qualitative match, it was a quantitative confirmation. The pattern in the sky was a direct photograph of reality itself coming into being. While the cosmologists were finding fractals at the edge of time, the particle physicists at CERN were preparing their own assault on the unknown. The initial discovery of a causal muons was tantalizing, but the statistics were limited. The produce astronomy. They had been found in the debris of the most energetic collisions, but their appearance was still rare, making it difficult to study their properties in detail. The community needed more of them. The solution was to push their magnificent machine to its absolute design limits. The Large Hadron Collider was upgraded, its magnets supercharged to increase the collision energy by a further 15%. The goal was to create a fire so hot, a density so extreme, that the fabric of spacetime would not just crack but tear open, providing a clearer gateway to the substratum. The experiment was a success. The higher energy collisions began to produce a causal muons not as a rare anomaly, but as a regular, predictable feature of the data. The production rate increased exponentially with the collision energy, just as one would expect if they were being created by a process that required piercing a barrier. With this new wealth of data, the physicists could finally begin to dissect the anatomy of their impossible particles, and they discovered a pattern that was even more shocking than their premature decay: the degree of their acausality. The precise amount of time by which they seemed to violate the normal sequence of cause and effect was not a fixed number. It varied from one event to the next, but it was not random. The team plotted the degree of acausality against the total energy of the collision that produced it, and the points on the graph did not form a scattered cloud. They formed a perfect, straight line, a direct, linear correlation. The more energy you pumped into the collision, the further outside of time the muons seemed to travel. This was the quantitative link they had been searching for. It was the experimental proof that energy, pure, raw energy, was the key that unlocked the door to the substratum. It was like discovering that the harder you press on a wall, the more your hand passes through it. The relationship between energy and acausality was a new law of nature, a law that could only be explained if energy itself was the currency that allowed temporary access to the timeless realm. The causal substratum was not just a passive ocean of potential. It was a dynamic reality with which our universe could interact if you could only pay the price of admission. And the price was energy. The correlation provided a powerful new tool. Physicists could now predict exactly how a causal, a muon, would be based on the energy of the collision that created it. This predictive power moved the phenomenon from the realm of anomaly to the realm of testable, repeatable science. But the final and most powerful piece of this deeper convergence came when these two worlds, the cosmic and the quantum, were finally brought together. The new, high-resolution map of the zero-point echo from the South Pole temporal array was not just a picture, it was a map of intensity. It showed where the pretemporal signal was strongest and where it was weakest. At the same time, new galactic surveys using automated telescopes to map the positions of millions of galaxies were creating the most detailed 3D maps of the cosmic web ever assembled. These maps allowed astrophysicists to chart the precise locations and boundaries of the great cosmic voids with unprecedented accuracy. They could now see which voids were the largest, which were the emptiest, and which were expanding the fastest. The two teams, Thorne's cosmologists and the astrophysicists mapping the voids, decided to compare their maps. It was a long shot, a search for a correlation between a signal from 13.8 billion years ago and the distribution of galaxies in the modern universe. There was no reason to expect a connection unless the causal substratum hypothesis was correct, unless the echo and the voids were two different symptoms of the same underlying cause. When they overlaid the two maps, a pattern of such profound and unambiguous clarity emerged that it left both teams in stunned silence. The correlation was perfect. The regions of the sky with the most intense, most powerful signal from the zero-point echo aligned perfectly with the locations of the largest, fastest expanding cosmic voids. It was not a statistical hint, it was a one-to-one correspondence. Where the sound of freezing was loudest, the ice of spacetime was weakest. The largest bubbles, trapped in the crystal of spacetime, were located precisely where the crystallization process had been most violent. It was like finding that the locations of all the major volcanoes on Earth perfectly matched the locations of ancient, buried impact craters. It would be an undeniable link between a surface feature and a deep, historical cause. This spatial correlation was the ultimate confirmation that the voids were not just empty space. They were a direct consequence of the same primordial event that created the zero-point echo. They were scars on the fabric of reality, remnants of the imperfect freezing of our universe, the anomalous expansion of the voids. The outward push that astronomers had measured could now be understood. It was the uncrystallized substratum, more energetic and more fundamental than our space-time, pushing on the boundaries of its cosmic prison. This connection provided a stunning unification of physics across all scales. A pattern in the oldest light in the universe was directly, physically linked to the distribution of galaxies billions of years later. A signal from before time was shaping the structure of the cosmos today, and a tiny particle breaking the rules of causality in a laboratory in Switzerland was the quantum echo of these same cosmic processes. The convergence was now so deep, so multifaceted, and so quantitatively precise that the causal substratum hypothesis was no longer on trial. It was beginning to look like the bedrock of a new reality. The dawn had broken. The new continent was not just visible, its mountains and rivers were now on the map. And yet, the most shocking discovery was still to come, from a field of science so far removed from cosmology that no one could have ever predicted it would hold the final key. A key that suggested this new reality was not just a feature of the cosmos, but a fundamental part of life itself. The history of science is a history of unexpected connections, of bridges being built between islands of knowledge that were once thought to be eternally separate. The laws of celestial mechanics, discovered by observing the planets, turned out to govern the fall of an apple on Earth. The physics of electromagnetism, developed to understand circuits and magnets, revealed the true nature of light. Time and again, the deepest truths about our universe have been found not by digging deeper in one place, but by recognizing a hidden pattern that connects them all. The causal substratum hypothesis had now built bridges between the birth of the cosmos, the death of a particle, and the great empty voids between the galaxies. It was a grand unification. But the final bridge, the one that would anchor this new reality not just in the cold equations of physics, but in the warm, messy reality of our own existence, would come from the most improbable field of all. It would come from the study of life itself. Our journey now takes us into the heart of a living cell, into the microscopic machinery of photosynthesis. For billions of years, plants and algae have been performing a trick that still borders on magic. They capture the energy of a photon of light from the sun and, with near-perfect efficiency, convert it into chemical energy, the fuel that powers almost all life on Earth. For decades, we understood the basic chemistry of this process. But the physics of it, the way a single photon's energy is captured and transported through the complex molecular architecture of the cell, remained a deep mystery. The problem is one of efficiency. When a photon strikes a chlorophyll molecule, it excites an electron to a higher energy state. This packet of energy, called an exciton, must then navigate a dense, chaotic forest of other molecules to reach the reaction center, the specific place where its energy can be converted into stable chemical form. The journey is treacherous, the cellular environment is warm and noisy. The exciton could easily lose its energy as heat, or get trapped in a dead end. Classical physics predicted that this process should be incredibly inefficient. The energy should dissipate long before it reaches its destination. Yet, in reality, photosynthesis is more than 95% efficient. The energy almost never gets lost. It was as if the exciton knew the one perfect direct path through the molecular maze. The solution to this mystery came from the strange world of quantum mechanics. Biologists discovered that the exciton does not travel along a single path. Like a quantum particle, it travels along every possible path simultaneously. It exists in a quantum superposition, a cloud of probability that spreads through the molecular forest, allowing it to feel out the entire landscape at once and instantly identify the most efficient route to the reaction center. It is an act of quantum computation performed by a living organism. But as scientists built more sophisticated models of this process, they ran into a new and even more profound impossibility: the speed of the computation. The process of finding the optimal path through the molecular maze is a classic and very difficult optimization problem. For a computer to solve it, it would have to check a vast number of possible routes. Even a quantum computer would require a certain amount of time to perform this search. But the energy transfer in photosynthesis happens in femtoseconds, quadrillionths of a second. It happens faster than light could even travel across the molecular complex, let alone perform the necessary computation. The cell was getting the right answer, but it was getting it faster than the speed of light seemed to permit within its own physical structure. A team of quantum biologists working on this problem stumbled upon the burgeoning literature of the causal substratum hypothesis. At first, they dismissed it as a bizarre cosmological speculation, irrelevant to their work. But the concept of a timeless, information-rich reality, a substrate where all causal pathways were simultaneously accessible, resonated with their impossible data. They began to wonder, what if the cell's quantum computer wasn't just using the pathways available within our space-time? What if it had, through billions of years of evolution, learned to perform the same trick as the causal muons? What if it had learned to tunnel its computations for an infinitesimal moment into the causal substratum? In the substratum, there is no time. An optimization problem that would require sequential steps in our reality could be solved instantly. The timeless, parallel processing nature of the substratum would be the ultimate supercomputer. The team developed a new model of photosynthesis, one that allowed the exciton's quantum state to briefly interact with the substratum. The results were astonishing. The model not only explained the impossible speed and efficiency of the energy transfer, but it also reproduced subtle, previously unexplained experimental data with perfect accuracy. They called the effect biological substratum tunneling, and its implications were staggering. It suggested that life itself, at its most fundamental level, is not just a phenomenon of our space-time. It has evolved to be a bridge between our temporal reality and the timeless reality that lies beneath. It was as if life, in its relentless drive for efficiency and survival, had discovered the universe's ultimate cheat code. It had learned to access a realm where the limitations of time and space do not apply. This was no longer just about physics. This was about us. The very process that powers the green leaves on the trees outside our windows, the process that creates the oxygen we breathe, was now implicated in the deepest and most profound mystery of our cosmic origins. It was the final and most intimate piece of corroborating evidence. The ghost in the machine of the cosmos was also a ghost in the machine of life. While biologists were finding evidence of a deeper reality in the machinery of life, theoretical physicists were finding it in the machinery of the universe itself. The causal substratum hypothesis, born from the need to explain a single anomalous signal, was now being tested not just against data, but against the very foundations of physical law. A new generation of theorists began to ask a daring question. If our universe is a crystal that formed from a timeless liquid, could the properties of that crystal, the fundamental constants of nature, be derived from the geometry of the crystallization process itself? For a century, the fundamental constants have been the sacred and deeply frustrating numbers of physics. The fine structure constant, which governs the strength of electromagnetism, the gravitational constant, the mass of the Higgs boson. These are numbers that we can measure with incredible precision, but we have no idea why. They have the values they do. They appear to be arbitrary, brute facts about our universe. Change any one of them by a tiny fraction, and the universe as we know it, with stable atoms, long-lived stars, and the possibility of life, could not exist. This fine-tuning problem has long been one of the deepest mysteries in science, pointing either to an incredible coincidence, the existence of a multiverse where all possible values are tried, or the hand of a creator. But the crystallization model offered a fourth and far more scientific possibility. The properties of a crystal, its hardness, its transparency, its electrical conductivity, are not arbitrary. They are determined by the geometry of its internal lattice, the specific way its atoms are arranged. Perhaps the fundamental constants of our universe are not arbitrary numbers at all. Perhaps they are the geometric properties of our four-dimensional spacetime crystal. The theorists began to build mathematical models of the crystallization of spacetime. They treated the substratum as a fluid of pure information, and the Big Bang as the moment this fluid began to lock into a stable, four-dimensional lattice. They explored different possible geometries for this crystal, different ways the atoms of spacetime could be arranged, and they made a discovery that sent shockwaves through the entire field of physics. One specific, highly symmetrical geometric structure, a four-dimensional analog of a quasi-crystal, did not just produce a stable, expanding universe. It produced a universe whose emergent geometric properties, when translated back into the language of physics, were the fundamental constants of our universe. The fine structure constant, for example, emerged as a simple ratio of geometric lengths within the crystal's unit cell. The mass of the Higgs boson was determined by the tension in the crystal lattice. The equations did not just approximate the constants. They derived their measured values from pure geometry, from first principles, with no arbitrary inputs. It was like discovering that the value of pi was not just a random string of numbers, but could be derived from the fundamental definition of a circle. The fine-tuning of the universe was not a coincidence. It was a consequence of its underlying geometry. Our universe is habitable because it is based on a particularly elegant and stable crystalline form. This was the final, global consilience, the ultimate unification. The zero-point echo from cosmology was the sound of the crystal forming. The causal muons from particle physics were quantum stress fractures in its lattice. The anomalous expansion of cosmic voids in astrophysics were trapped pockets of uncrystallized liquid. The impossible efficiency of photosynthesis in biology was life learning to exploit the crystal's connection to its liquid origin. And now, the fundamental constants of nature from theoretical physics were the geometric ratios of the crystal itself. Evidence from every major field of natural science, from the study of life to the study of the entire cosmos, from the infinitesimally small to the infinitely large, was now pointing to the same, single, revolutionary conclusion. The causal substratum was real, our universe was a crystal, and the story of our origins was not what we thought. The inferential net had closed. The puzzle pieces, gathered from a dozen different rooms of the House of Science, had now been assembled, and they formed a single, coherent, and terrifying picture. The hypothesis had transformed from a fringe idea into the central, organizing principle of a new and profound understanding of reality. The paradigm had shifted, and now, the real work could begin, the work of proving it wrong. Science is not a gentle process of accumulating facts, it is a battlefield. Every great leap forward in our understanding of the universe was born in conflict, in the brutal, systematic attempt by the scientific community to destroy the very idea that would later become its foundation. A theory that cannot withstand the most ferocious and intelligent attacks is not worthy of belief. Before the causal substratum hypothesis could be accepted as a new paradigm, it had to survive trial by fire. It had to face the organized institutional skepticism that is the immune system of science, a system designed to identify and eliminate flawed ideas before they can infect our understanding of reality. The evidence was compelling, the convergence was beautiful, but was it real? Or was it an illusion, a grand coincidence born of subtle errors, hidden biases, and the all-too-human desire to find patterns in the noise? To answer this, the global physics community organized one of the most extraordinary and ambitious tests of a scientific theory ever conceived. It was called an adversarial collaboration. This is a process reserved for the most contentious and high-stakes debates in science, a last resort when a field is split into warring factions. The concept is simple, but its execution is a profound act of intellectual honesty. You take the leading proponents of the new theory and you lock them in a room with its most brilliant and ferocious critics. You give them both equal access to all the raw, unadulterated data from every experiment, and you give them a single, shared task: reanalyze everything from scratch, together, checking each other's work at every step. The goal is not to find a compromise. The goal is to find the truth, even if it means proving yourself wrong. Two teams were formed. One was led by Dr. Aris Thorne himself, the reluctant prophet of this new cosmology. The other was led by a notoriously brilliant and skeptical physicist who had publicly called the substratum hypothesis an elegant fantasy, a return to pre-scientific mysticism. They were given the full, raw data streams from the Planck Deep Field Array, the South Pole Temporal Array, and the relevant experiments at the Large Hadron Collider. Nothing was pre-processed. Nothing was cleaned. They were given the ones and zeros, the direct, unfiltered output from the machines themselves. The process was brutal. Every line of analysis code was scrutinized. Every statistical assumption was challenged. Every potential source of instrumental error, no matter how remote, was modeled and tested. The proponents were forced to defend their methods against the most intelligent and motivated attacks imaginable. The skeptics were forced to confront, step by step, the stubborn persistence of the anomalies in the data. They started with the zero-point echo. The skeptical team was convinced it was a subtle artifact of the data processing, a phantom created by the complex algorithms used to subtract the foreground light of our own galaxy. They spent months developing new, more sophisticated algorithms, absolutely certain that with better cleaning techniques, the signal would vanish. It did not. In fact, under their more rigorous analysis, the signal became even sharper, its fractal structure even more pronounced. It was the first moment of shock for the skeptical team. Their best weapon had not only failed to kill the anomaly, it had made it stronger. Next, they turned to the causal muons. The skeptics' primary argument was that this was not a violation of causality, but a subtle, misunderstood detector effect. Perhaps the muons were not decaying early, but were being created in a different part of the collision than the models assumed, giving them a head start on their journey to the detectors. The collaboration designed a new set of experiments at the LHC, placing additional, high-precision timing detectors closer to the collision point. This would allow them to triangulate the exact origin point of the muons with unprecedented accuracy. The results came back, and they were unambiguous. The muons were being created exactly where the standard model predicted. They were not taking a shortcut through space. They were taking a shortcut through time. Another major line of skeptical attack had collapsed. The atmosphere in the collaboration began to shift from one of open conflict to one of shared and deeply unsettling discovery. These were not enemies anymore. They were fellow investigators, standing together before the same impossible crime scene. Finally, they conducted a blind analysis. This is the gold standard of scientific rigor. One part of the team, composed of both proponents and skeptics, would take the raw data and deliberately add a fake, artificial signal to some of it, while leaving other parts untouched. They would then give this, salted, data to the rest of the team, without telling them which datasets were which. The job of the analysis team was to see if they could find the real anomalies while correctly identifying and discarding the fake ones. It is a test designed to mercilessly expose confirmation bias, the tendency to see what you expect to see. If the analysts found fake signals where there were none, or missed the real ones, the entire methodology would be proven unreliable. The process took over a year, and when the results were unblinded, they were stunning. The analysis team had found the real zero-point echo and the real causal muon signals in every single dataset where they were present, with 0 false positives, and they had correctly identified every single one of the artificially injected fake signals. The methodology was sound, the anomalies were not a product of bias. They were a feature of reality. The final report from the adversarial collaboration was a landmark document in the history of science. It concluded, with the unanimous agreement of both the proponents and the initial skeptics, that the anomalies were real, statistically significant, and not attributable to any known instrumental or analytical error. The document did not endorse the causal substratum hypothesis. That was not its job. Its job was simply to validate the evidence. But in doing so, it left the scientific community with an undeniable and deeply uncomfortable truth. The universe was not behaving as it should. The crime was real. Now, the search for the perpetrator could begin in earnest. Even with the evidence validated, the war for the soul of physics was not over. It simply moved to a new battlefield. The anomalies were real, but did they truly require such a radical explanation as a pre-temporal reality? Science, guided by the principle of Occam's razor, always prefers the simplest explanation that fits the facts. Before embracing a new layer of existence, every possible explanation within the existing framework had to be exhausted. This led to a new phase of the investigation, the design of null tests. A null test is an experiment designed not to prove a theory right, but to prove it wrong, by looking for its effects in a place where the theory predicts they absolutely should not exist. If you find the effect there, your theory is broken. The causal substratum hypothesis, with its specific and unusual predictions, was a perfect candidate for this kind of targeted assault. The first and most powerful null test was designed at CERN. The hypothesis was clear. Causal muons only appear when a particle collision is energetic enough to crack space-time and open a gateway to the substratum. This implied that there should be a sharp energy threshold. Below that threshold, reality should behave perfectly normally. No matter how many collisions you create, no matter how much data you collect, you should find 0 causal muons. It was a bold, black and white prediction. The skeptics saw this as the theory's Achilles heel. They designed an experiment to run the LHC at a range of energies just below this predicted threshold. If they could find even a single causal muon at these lower energies, it would prove that the phenomenon was not a threshold effect, but some other, more continuous process that the substratum model could not explain. The experiment ran for 6 months. Billions upon billions of proton collisions were recorded and analyzed. And the result was a perfect, resounding silence. Not a single causal muon was detected below the threshold. Then, as they slowly ramped the energy up, the moment the collider crossed the predicted energy level, the causal muons began to appear in the detectors, exactly as the theory foretold. The null test had failed to break the hypothesis. Instead, it had provided its most stunning confirmation yet. A second null test was designed for the cosmologists. If the zero-point echo was a real, primordial signal imprinted on the very fabric of space-time, then it should be universal. It should be detectable not just in the light of the CMB, but in other cosmological backgrounds as well. One such background is the cosmic neutrino background, a sea of ghostly low-energy particles that fill the universe, left over from the first second of the Big Bang. These neutrinos decoupled from normal matter even earlier than the CMB photons, so they carry a snapshot of an even earlier epoch. Detecting them directly is almost impossible. But the hypothesis predicted that the same crystallization event that polarized the light of the CMB should have also left a subtle imprint on the spatial distribution of these primordial neutrinos. A new generation of neutrino observatories, vast arrays of detectors buried deep under the Antarctic ice and the Mediterranean Sea, began to search for this effect. The theory predicted a subtle anisotropy, a slight preference for neutrinos to be coming from the same directions as the strongest parts of the zero-point echo. If the neutrinos were perfectly isotropic, perfectly uniform from all directions, the hypothesis would be in serious trouble. After years of collecting data, the first maps of the cosmic neutrino background were produced. They were blurry, low-resolution images, but even in the noise, a pattern was visible. There was a clear, statistically significant excess of neutrinos coming from the very same regions of the sky where the echo was strongest. The second null test had failed. The universe was speaking in multiple languages, the language of light and the language of neutrinos, and it was telling the same story. With the hypothesis surviving these direct attacks, the final line of defense for the old paradigm was to argue that even if the anomalies were real, they did not necessarily belong to the substratum theory. The global scientific community now had access to all the validated data. The race was on. Could anyone, anywhere in the world, construct a plausible model from within standard physics that could explain the fractal echo, the energy-dependent acausal muons, and the correlation with cosmic voids, all at the same time? It was a challenge thrown down to the entire intellectual resources of the human species. Thousands of papers were published. Computer simulations ran for millions of processor hours. Every corner of theoretical physics was ransacked for a possible solution. Models involving complex modifications to cosmic inflation were proposed. Others explored Baroque extensions of string theory with intersecting branes. Still others suggested that dark matter might have previously unknown properties that could generate these effects. But each of these models suffered from the same fatal flaw. While they might be able to explain one of the anomalies, they could not explain all three simultaneously without becoming monstrously complex and fine-tuned. To explain the echo, you had to add new fields to inflation that then failed to explain the muons. To explain the muons, you had to modify relativity in ways that violated the CMB data. Every attempt was like trying to cover a body with a blanket that was too small. Pull it over the head, and the feet are exposed. Cover the feet, and the head is left in the cold. Only the causal substratum hypothesis provided a single, simple, and elegant blanket that covered everything. Its core idea, that spacetime is a crystal that froze from a timeless liquid, naturally and inevitably predicted all three anomalies from one foundational concept. After years of this intense global effort, a consensus began to emerge, not of enthusiastic acceptance, but of reluctant necessity. No other theory worked. The causal substratum model was the only game in town. The evidence had been stress-tested against every conceivable methodological, instrumental, and theoretical challenge. It had been attacked by the brightest minds in the field, and it had not just survived, it had grown stronger with every test. The robustness of the case was no longer in question. The era of doubt was over. The era of confrontation, of facing the profound and terrifying implications of this new reality, was about to begin. But a revolution is never bloodless. Even as a new consensus began to form around this extraordinary picture of reality, the old paradigm did not die quietly. Science is a human endeavor, and it is subject to the same inertia, the same passions, and the same fierce attachments to established ideas as any other part of our culture. For many physicists, the causal substratum hypothesis, despite its growing body of evidence, represented a bridge too far. It was not just a new chapter, it was a different book, written in a different language, and they were not yet ready to abandon the library they had spent their lives building. The time had come for the counterattack, for the old guard to mount its last, most intelligent, and most desperate defense, and in doing so, they would expose the true weaknesses and the remaining profound questions that still haunted this emerging new reality. The first and most powerful counterargument was not about the data, but about the very nature of science itself. It was a philosophical objection, but one with the sharp, deadly edge of methodological rigor. The most respected and conservative voices in the physics community leveled a profound charge. The causal substratum, they argued, was fundamentally unscientific. By its own definition, it was a timeless, spaceless realm of pure information that existed before our universe. How, they asked, can you ever claim to have a scientific theory about a place that is, by definition, unobservable? Science, they reminded the world, deals with the empirical, the measurable, the testable. We build theories about the universe we can see. A theory that posits an entire layer of existence beyond any possibility of direct detection is not physics. It is metaphysics. It is philosophy masquerading in the language of mathematics. This was not a trivial objection. It struck at the very heart of what it means to do science. Think of it like this. Imagine a detective trying to solve a murder. All the evidence, the fingerprints, the timeline, the weapon, points to a suspect who is, according to every law of logic and physics, a ghost, a non-physical entity. The detective might have a perfect case that the ghost is the killer, but at what point does the investigation cease to be a police matter and become a question for a priest or a philosopher? The critics of the substratum hypothesis argued that Thorne and his followers had crossed that line. They had invoked a ghost to explain the mysteries in our universe. They had abandoned the core principle of scientific naturalism, the idea that all phenomena can be explained by natural causes within our universe, and had instead pointed to a supernatural cause, a cause from outside of nature itself. The argument was steel-manned with precision. The proponents of the hypothesis could point to the echo, the muons, the voids. But these, the critics argued, were merely the effects within our universe. The cause, the substratum itself, remained forever beyond our grasp. You could never build a probe to visit it. You could never capture a piece of it in a bottle. Its existence could only ever be inferred, never directly verified. This, they claimed, made the theory dangerously unfalsifiable at its core. If any future experiment failed to find a predicted effect, the proponents could always argue that the interaction with the substratum was simply too weak to be detected, or that the conditions weren't quite right. A theory that can't be proven wrong, the old saying goes, is not a scientific theory at all. It is a belief system. The charge was that crystallizing space-time cosmology was not the next great leap in physics, but a regression, a return to the pre-scientific age of invoking unknowable, transcendent realms to explain the mysteries of our own. It was a beautiful story, they admitted, but it was not science. While the philosophers of science debated the soul of their field, a different, more concrete attack was being launched from within the heart of physics itself. A powerful group of theorists focused their attention on the causal muons. They conceded that the timing anomaly was real, that the adversarial collaboration had proven it beyond doubt. But they offered a different, and in their view, far more conservative explanation. The muons were not evidence of a pre-temporal reality, they argued. They were the first sign of a breakdown in one of the most sacred principles of modern physics, Lorentz invariance. Lorentz invariance is the mathematical heart of Einstein's theory of special relativity. It is the principle that states that the laws of physics are the same for all observers, regardless of their constant velocity. It is the foundation upon which our understanding of space, time, and causality is built. It is the reason why the speed of light is an absolute cosmic speed limit. For a century, this principle had been tested to an extraordinary degree of precision and had never been found wanting. What, the critics argued, what if it is not absolute? What if, at the almost unimaginable energies created in the LHC collisions, energies not seen since the first moments of the Big Bang, this fundamental symmetry of nature begins to fray? A tiny breakdown in Lorentz invariance could, theoretically, allow for apparent violations of causality without requiring a whole new layer of reality. It would mean that at extreme energies, the rigid link between cause and effect might become slightly flexible. Information might be able to take subtle shortcuts through spacetime, appearing to travel faster than light. It would be a revolution in physics, a discovery that would undoubtedly win a Nobel Prize and force a complete rewrite of our understanding of relativity. But it would be a revolution within physics. It would be an extension of our current theories, not a complete replacement of them. It would be like discovering a new continent on Earth, a vast and unexplored land, but one that was still part of our world, still on our map. The causal substratum, by contrast, was the claim that a new map and a new world existed entirely. The skeptics argued that this was the more scientific, more rational path. Before you claim to have found a ghost, you must first exhaust every possibility that you have simply misunderstood the laws that govern the house. The causal muons, they insisted, were not a message from outside of time. They were a message from the very edge of our understanding of time itself, a hint that our current laws are incomplete. They accused the substratum proponents of leaping to the most exotic and radical conclusion when a more sober, albeit still revolutionary, explanation was available. This argument was powerful because it was scientifically conservative. It did not require invoking unobservable realms. It only required modifying a known principle at an energy scale we had never before been able to test. It was an appeal to the core methodology of science. Extend the known before you invent the unknown. The final major line of attack was statistical. It was a cold, mathematical assault on the beautiful web of connections that the substratum's proponents had so carefully woven. The correlation between the zero-point echo, the anomalous expansion of cosmic voids, and the values of the fundamental constants was, the skeptics argued, a classic case of the Dweck, look elsewhere effect. This is a subtle but deadly trap in data analysis. If you have a vast amount of data and you search for enough different kinds of patterns, you are statistically guaranteed to find correlations that appear meaningful but are, in fact, purely coincidental. It is like firing a machine gun at the side of a barn and then drawing a bullseye around the tightest cluster of bullet holes. It looks like incredible marksmanship, but it is just an illusion created by cherry-picking the data. The critics argued that this is precisely what the proponents of the substratum had done. They had found 3 separate, unexplained anomalies in 3 vast and noisy datasets. They then proposed a single theory that connected them and claimed this connection as powerful evidence. But how many other potential correlations had they looked for and failed to find? How many other ways could these anomalies have been combined? In a universe of infinite data, you can find support for almost any theory if you are selective enough in what you choose to see as significant. The spatial correlation between the echo and the cosmic voids was particularly suspect. The maps were complex, the boundaries were fuzzy. Was the alignment really as perfect as claimed, or was it a case of motivated perception, of seeing a face in the clouds? The derivation of the fundamental constants from the crystal geometry was also attacked on these grounds. The mathematics was complex. Were there other geometric models that could also produce these numbers? Had the theorists simply stopped looking once they found a model that seemed to work? This statistical critique was the most difficult to refute because it cast doubt not on the data itself, but on the human interpretation of that data. It suggested that the beautiful convergence of evidence was not a feature of the universe, but a feature of the human mind, our innate and often misleading talent for finding patterns in randomness. The skeptics laid down a final, brutal challenge. They demanded a clear, single, unambiguous prediction. Not a post hoc explanation of existing data, not a correlation that could be dismissed as a statistical fluke. They wanted the theory to point to something that had not yet been seen, something that could be searched for, found, and which, if it existed, could have no other plausible explanation. They wanted the theory to step out from behind the shield of its existing evidence and face the cold, hard judgment of a future, unknown observation. It was the ultimate ultimatum. The theory had to make a prophecy, and if that prophecy failed, it would be the end of the revolution. Faced with a coordinated assault on its very legitimacy, the causal substratum hypothesis had to do more than simply rest on its laurels. It had to fight back, not with rhetoric, but with data and logic. The counterarguments were not frivolous, they were sharp, intelligent, and they exposed the genuine frontiers of this new science. Dr. Thorne and the growing community of researchers exploring this new paradigm met each challenge head-on in a period of intense debate and discovery that would refine the boundaries of the theory and ultimately solidify its place as the successor to the Standard Model. The first charge, that the hypothesis was fundamentally unscientific because the substratum itself is unobservable, was the most profound. It was a challenge that could not be answered with a simple experiment, but required a new argument about the nature of scientific inference itself. Thorne's team offered a powerful rebuttal. They drew an analogy to the discovery of the electron over a century earlier, when J.J. Thomson first proposed the existence of this tiny negatively charged particle. No one had ever seen one. No one ever has. An electron is a point-like entity with no size, a phantom that exists as a cloud of probability. It is, in a very real sense, unobservable. What Thomson saw were the effects of the electron, the way cathode rays bent in a magnetic field, the specific charge to mass ratio he could measure. Science, they argued, has always progressed by inferring the existence of unobservable entities to explain observable phenomena. We do not see quarks, but we see the patterns they create in particle collisions. We do not see the quantum wave function, but we see the interference patterns it produces. We do not see the curvature of spacetime, but we see the orbit of Mercury and the bending of starlight. The causal substratum, they contended, was no different. It was an inferred entity, but it was inferred from a wealth of precise, observable, and testable effects within our own universe. The zero-point echo, the acausal muons, the anomalous expansion of voids, these were the cathode rays of the 21st century. They were the observable phenomena that demanded a new, underlying cause. To declare the substratum unscientific, simply because we cannot visit it, was to misunderstand the very nature of inference, the engine of all modern physics. Science is not just about what we can see, it is about building logical structures that can explain what we see. The substratum was just such a structure. And unlike a purely philosophical claim, it made predictions about the world that could be tested and, crucially, could be falsified. The theory was not a retreat into metaphysics, it was an expansion of physics into a new and deeper territory, guided by the same principles of evidence and logic that have always defined the scientific endeavor. The second challenge, the idea that the acausal muons were not evidence of substratum tunneling, but of a breakdown in Lorentz invariance, was more concrete and required a direct experimental rebuttal. The idea of Lorentz violation was, in its own way, just as revolutionary as the substratum. It would mean that Einstein's special relativity was not a fundamental truth, but an approximation that fails at extreme energies. The key to distinguishing between these two radical ideas was to find a feature that one theory predicted and the other did not. Thorne's team found one in the details of the acausal muon phenomenon itself. If the effect was a general breakdown of relativity, a fraying of spacetime's fundamental rules, then it should affect all particles more or less equally. At a certain energy, all particles should begin to exhibit subtle acausal behaviors. It would be like a speed limit that starts to get fuzzy for all vehicles once they reach a certain velocity. But the causal substratum model predicted something far more specific. The ability to tunnel into the substratum would not be a universal property of energy, but a specific property of a particle's quantum structure. Just as only certain particles can interact through the strong nuclear force, perhaps only certain particles could interact with the substratum. The mathematics of the crystallization model suggested that particles with a specific kind of quantum spin and a particular relationship to the Higgs field, properties possessed by muons, but not, for example, by their lighter cousins, the electrons, would be far more likely to tunnel. It was a highly specific and risky prediction. A new series of experiments were designed at the LHC. This time, they would not just look for a causal muons. They would collide electrons and positrons at the same extreme energies and search for a causal electrons. According to the Lorentz violation model, they should be there. The rules of spacetime should be breaking down for them too. According to the substratum model, they should not. After a year of running the collider in this new mode and sifting through mountains of data, the results were in. Causal muons continued to appear in proton-proton collisions at the expected rates, but in the electron-positron collisions, at the exact same energy levels, there was nothing. Not a single causal electron was ever detected. The effect was particle-specific. It was not a general breakdown of spacetime, it was a specific interaction, a specific capability possessed by certain types of matter. The Lorentz violation argument, while elegant, was now decisively weakened by the data. The evidence was pointing not to a flaw in our spacetime, but to a connection to something beyond it. Finally, the proponents had to confront the most insidious and difficult challenge of all, the "look elsewhere" effect. The charge that their beautiful convergence of evidence was a mere statistical illusion, a pattern they had imposed on the noise. This could not be answered with a single experiment. It had to be answered with a brutal application of probability theory. The team took on the challenge directly. They agreed, for the sake of argument, that each of the three primary anomalies, the echo, the muons, and the voids, could, in isolation, be a 1 in a million statistical fluke. This was a generous concession, as the data suggested they were far more unlikely than that. But even with this assumption, what was the probability of all three of these unrelated 1 in a million flukes occurring simultaneously? The answer is a simple multiplication of probabilities. 1 in a million times 1 in a million times 1 in a million. The result is a number so infinitesimally small, 1 in a quintillion, that to believe it was a coincidence was to abandon statistical reasoning altogether. It would be like winning the lottery every day for a week. At some point you must conclude that the game is rigged. But they knew this argument, however powerful, would not be enough. The skeptics had thrown down the gauntlet. They had demanded a single, unambiguous prediction, a smoking gun, an observation that could not be explained away as a statistical artifact or a modification of known physics. Thorne and his team retreated, and for months, the community waited. They were deep within the mathematics of their crystallization model, searching for a unique, unavoidable consequence of spacetime freezing into existence. They were looking for the one signature that a chaotic, inflationary Big Bang could never produce, but that a structured, crystallizing Big Bang must, and then they announced it. It was a prediction of breathtaking audacity, targeting a phenomenon that had not even been definitively detected yet: primordial gravitational waves. Gravitational waves are ripples in the fabric of spacetime itself. Both standard inflation and the crystallization model predicted that the violent birth of the universe should have created a background of these waves, a gravitational wave equivalent of the cosmic microwave background. Detecting this background hiss was the next great quest in cosmology. But Thorne's team predicted that the gravitational waves from a crystallization event would have a unique property that inflationary waves would not. They would be chiral. Chirality is the property of handedness. Your left hand and your right hand are mirror images, but they are not identical. You cannot superimpose one on the other. A chiral gravitational wave is one that spirals through space with a specific handedness, either clockwise or counterclockwise. Standard inflation, being a chaotic random process, should produce an equal mixture of left and right-handed waves, resulting in a background that has no net chirality. But a phase transition, a crystallization event, is a process that can break symmetries. Just as a crystal can have a specific handedness in its lattice, the shock wave from the freezing of spacetime would, according to their model, inevitably produce gravitational waves with a dominant twist, a net chiral polarization. This was the prophecy, a single, clear, binary prediction. If the primordial gravitational wave background was ever detected and found to be non-chiral, the causal substratum hypothesis would be dead. But if it was found to have the specific twisted signature their model predicted, it would be the smoking gun. It would be a fingerprint that no other suspect could have left at the scene of the crime. The challenge had been met. The debate was no longer about the past. It was now a race to the future, a race to build the instruments that could finally read this ultimate signature from the moment our universe was born. The war was over. Not with a final climactic battle, but with the slow, dawning acceptance that the landscape of reality had irrevocably changed. The evidence, having survived every trial and every attack, now stood as a set of established facts. The zero-point echo was real, the acausal muons were real, the anomalous voids were real. The old story of our origins, the simple, elegant narrative of a universe born from a single point in time, was no longer sufficient. It was not necessarily wrong, but it was profoundly incomplete. It was a single chapter from a much larger book. The task now facing science was no longer one of conflict, but of construction. The old house of cosmology had been shaken to its foundations. It was time to build a new one, a grander structure that could contain these strange new truths. It was time for synthesis. With the major objections addressed and a clear, high-stakes prediction on the table, the causal substratum hypothesis moved from the fringe to the center of theoretical physics. The period of intense debate gave way to a period of intense model building. The goal was no longer just to prove the idea, but to flesh it out, to transform a compelling hypothesis into a comprehensive, mathematically rigorous framework that could not only explain the known anomalies, but also serve as a guide to the unknown. This new framework was given a name that captured its central revolutionary idea: crystallizing space-time cosmology. It was a theory built on the ashes of the old certainties, a new narrative for a universe that was suddenly far older and far stranger than we had ever imagined. The first task was to integrate all the disparate threads of evidence into a single, coherent mathematical structure. This was a monumental undertaking, requiring the combined expertise of cosmologists, particle physicists, and condensed matter theorists, experts in the physics of phase transitions and crystallization. They began with the heart of the theory, the causal substratum itself. For decades, physicists searching for a theory of everything had explored ideas like string theory and loop quantum gravity, which treated the fundamental constituents of reality as tiny vibrating strings or discrete loops of spacetime. Crystallizing spacetime cosmology took a different approach. It proposed that the most fundamental layer of reality is not geometric, but informational. The substratum was modeled not as a physical space, but as an abstract computational space, a network of pure causal relationships. Think of it as the ultimate computer, a system whose hardware is logic itself, running every possible program simultaneously in a timeless, parallel state. Each program is a self-consistent set of mathematical rules, a potential universe. Within this framework, the Big Bang was modeled as a specific type of computational event, a spontaneous symmetry breaking. In the timeless, hypersymmetrical state of the substratum, all possible laws of physics exist in a perfect, undifferentiated equilibrium. The crystallization event was the moment a random fluctuation broke that symmetry, selecting one particular set of rules, one program, and causing it to execute. The execution of that program, the unfolding of its rules in a logical sequence, is our spacetime. The emergence of the arrow of time is the computer processing its instructions, one step after another. This model provided a new and deeply powerful language for describing our origins. It replaced the fuzzy, quasi-mystical concept of a singularity with the precise, well-understood mathematics of computational phase transitions. This new language allowed for a stunning unification of phenomena at wildly different scales. The model was like a Rosetta Stone, allowing physicists to translate between the language of the quantum world and the language of the cosmos. At the smallest scales, it provided a complete and predictive theory of the causal muons. In the model, elementary particles are not fundamental entities, but persistent computational patterns, stable knots, in the logic of the spacetime crystal. The intense energy of an LHC collision was modeled as a localized heating of the crystal, causing it to momentarily melt back into the liquid state of the substratum. The model predicted, with stunning accuracy, the exact energy threshold required for this melting to occur. Furthermore, it explained the particle specificity of the effect, the quantum properties of muons made their knots particularly susceptible to unraveling in this melted state, allowing them to access the timeless computational pathways of the substratum, while the more stable knots of electrons remained intact. The theory didn't just explain the anomaly, it predicted its precise characteristics from first principles. This same framework provided a new and profound understanding of one of quantum mechanics' oldest and strangest mysteries, quantum entanglement. Entanglement is the spooky action at a distance that so troubled Einstein. The fact that two particles can be linked in such a way that measuring a property of one instantly influences the other, no matter how far apart they are. In the standard model, this connection seems to violate the cosmic speed limit, but in crystallizing spacetime cosmology, there is no violation. The two entangled particles, while separated by vast distances in our crystallized spacetime, remain connected through the timeless substratum. The substratum is atemporal and non-local. Distance has no meaning there. The instantaneous connection is not a signal traveling faster than light through our universe. It is a single, timeless causal link in the underlying reality, a reality where here and there are the same. The theory transformed entanglement from a spooky paradox into a natural and necessary consequence of our universe's structure, a direct window into the timeless world that lies beneath. At the cosmological scale, the model provided a rich and detailed picture of our universe's birth and structure. The zero-point echo was now understood not just as a generic shockwave, but as the crystallization front, the precise boundary between the timeless substratum and our emergent spacetime, frozen into the cosmic microwave background. The fractal patterns discovered in the echo's polarization were a direct prediction of the cascading, branching nature of the crystallization process. The model's simulations of this process produced fractal dimensions that matched the observational data to within a few percent. The anomalous expansion of the great cosmic voids was also seamlessly integrated. They were no longer just bubbles of trapped liquid. They were regions where the crystallization process had stalled, leaving behind stable, supercooled pockets of the substratum. The model predicted that the surface tension between these pockets and the surrounding spacetime crystal would create a negative pressure, an outward push that would cause the voids to expand faster than the rest of the universe. It provided a physical mechanism for the anomalous expansion that did not require any modification to our understanding of dark energy. And finally, the model achieved the holy grail of theoretical physics. It explained the fine-tuning of the fundamental constants. As we saw, the theory proposed that the constants of nature are not arbitrary numbers, but are the emergent geometric properties of the specific crystalline lattice of our spacetime. The model of a four-dimensional quasi-crystal did not just happen to produce the right numbers. The theory now explained why. This specific crystal structure was selected out of all other possibilities during the phase transition. It was the most stable, most symmetric, and most informationally efficient structure that could form. Just as soap bubbles naturally form spheres because that is the lowest energy state for a given volume, our universe crystallized into the specific geometric form that was maximally stable. Our universe is hospitable to life not because it was designed for us, but because it settled into the most elegant and robust mathematical form possible. It was a single, coherent narrative that connected the deepest mysteries of the quantum realm to the grandest structures of the cosmos and the most fundamental numbers that govern our existence. It was a theory of everything, not in the sense that it answered all questions, but in the sense that it provided a single, unified foundation from which all the phenomena of our universe emerged. The new house of cosmology had been framed. Now it was time to test its integrity. A theory, no matter how elegant or comprehensive, remains a work of fiction until it makes contact with the future. A story about the past can always be rewritten, its details reinterpreted to fit the available clues. But a true theory of nature must do more than explain what we have already seen. It must predict what we have not. It must point to a new, undiscovered country and describe its features before our explorers ever set foot on its shores. The ultimate test of crystallizing spacetime cosmology was not how well it explained the past, but how accurately it could foretell the future of scientific discovery. With the model now fully assembled, a coherent framework that connected the pretemporal to the biological, it was time to derive its unique, non-negotiable predictions. It was time to give the skeptics the clear, unambiguous targets they had demanded. It was time to make a prophecy. The new model made two critical, near-term predictions. They were not vague or subtle. They were sharp, specific, and aimed directly at the next generation of scientific instruments that were already under construction. These were not predictions for a distant, unknowable future. They were wagers on the outcome of experiments that would be conducted within our lifetimes. The first, and most profound, was the prophecy that Dr. Thorne's team had used to answer their critics. It concerned the faint, ghostly whisper of primordial gravitational waves, the ripples in spacetime left over from the universe's violent birth. Standard cosmic inflation, the leading theory for decades, predicted that the Big Bang should have filled the universe with a background of these waves. But it predicted that this background would be random, a chaotic hiss of equal parts left-handed and right-handed spiraling waves. A process born of pure, unstructured quantum noise should have no preferred directionality. It would be an equal opportunity creator of gravitational twists. But crystallizing spacetime cosmology told a different story. The birth of our universe was not a chaotic explosion. It was a structured, orderly process, a phase transition. A crystallization. And just as the freezing of water breaks the perfect symmetry of the liquid to create a crystal with specific oriented axes, the freezing of spacetime from the causal substratum would have broken the fundamental symmetries of the pretemporal realm. The model predicted, with mathematical certainty, that this symmetry breaking would have a specific consequence. The shock wave of the crystallization front would have preferentially produced gravitational waves with one-handedness over the other. The primordial gravitational wave background must be chiral. It must have a net twist, a dominant spiral direction, either clockwise or counterclockwise. Think of the difference between the sound of a random explosion and the sound of a bell. The explosion is pure noise, a chaotic mix of all frequencies and phases. But the bell, because of its specific symmetric structure, rings with a pure, ordered tone. The standard model predicted that the sound of the Big Bang would be noise. The new model predicted it would be a clear, resonant tone, a single, cosmic note with a specific, measurable twist to its vibrations. This was the unambiguous prediction the skeptics had demanded. There was no wiggle room. No way to explain it away with complex astrophysics. A chiral gravitational wave background is forbidden by all standard inflationary models. Its detection would be a smoking gun, a definitive fingerprint of a crystallization event. If the next generation of gravitational wave observatories found a primordial background, but it was perfectly non-chiral, a 50/50 mix of left and right twists, then crystallizing spacetime cosmology would be dead on arrival. The entire edifice would crumble. The search for this signal required an instrument of almost unimaginable sensitivity. Ground-based detectors like LIGO are superb at detecting the violent, short-lived chirps from colliding black holes and neutron stars, but the primordial background is a faint, persistent hiss, a whisper billions of times weaker, stretched across the entire sky. To hear it, we would need to build a detector the size of the solar system. And that is precisely what humanity began to do. The plan was for an observatory called LISA, the Laser Interferometer Space Antenna. It would consist of 3 separate spacecraft, flying in a perfect triangular formation millions of miles apart, connected by laser beams. These lasers would act as the arms of the most sensitive gravitational wave detector ever conceived. As a gravitational wave passed through the formation, it would stretch and squeeze the fabric of space, minutely changing the distance between the spacecraft. LISA would be able to detect changes in distance smaller than the width of an atomic nucleus, across a baseline of millions of miles. It would be an instrument so sensitive it could hear the universe breathing. And its primary mission would be to search for the primordial gravitational wave background and to measure its polarization, to determine if the sound of creation was a random hiss or a pure, twisted, chiral tone. The prophecy had been made. The instrument to test it was being built. The fate of our understanding of cosmic origins now hung in the balance, waiting for a verdict that would come from the silence of deep space. But the model did not rest on a single, all-or-nothing bet. It made a second, equally bold and equally testable prediction. This one aimed not at the dawn of time, but at the great, empty voids of the modern universe. As we have seen, the hypothesis explained the anomalous expansion of these voids by proposing that they are not truly empty, they are unfrozen. Pockets of the causal substratum, trapped within the crystal of our spacetime. If this is true, then these voids are not just holes in the distribution of galaxies, they are fundamentally different regions of reality, operating under a different physical state. This difference should be measurable. The theory made a specific prediction about the nature of the quantum vacuum within these voids. In our crystallized spacetime, the quantum vacuum has a certain baseline energy level, the so-called zero-point energy. This is the minimum energy that space can have, the seething foam of virtual particles that exists even in perfect emptiness. This energy level is a fundamental property of our universe, determined by the structure of our specific spacetime crystal. But if the voids are pockets of uncrystallized substratum, then their vacuum state should be different. The substratum is a more primordial, more energetic state of reality. The model predicted that the zero-point energy of the vacuum inside a great void should be measurably higher than the zero-point energy of the vacuum in normal space, the space between galaxies in the cosmic web. It was a subtle difference, but a fundamental one. It would be like discovering that the temperature of the air inside a bubble trapped in ice is higher than the temperature of the surrounding ice. It would be proof that the bubble contained something different, something left over from a hotter, more energetic past. Detecting this difference, however, would be one of the most technologically challenging experiments ever attempted. The zero-point energy of the vacuum cannot be measured directly, but it can be measured indirectly through its effects on matter. One such effect is called the Casimir effect. As we have discussed, when two uncharged, parallel metal plates are placed very close together in a vacuum, the pressure of the virtual particles outside the plates is greater than the pressure between them, pushing the plates together with a tiny but measurable force. The strength of this force is directly proportional to the energy density of the quantum vacuum. The prediction was clear. If you could build a probe with a highly sensitive Casimir force detector and send it into the heart of a cosmic void, it should measure a slightly stronger force than a similar detector operating in the space between galaxies. It would be a direct measurement of the pressure of the uncrystallized substratum. This was the second great prophecy of the new cosmology. The plan was audacious. It called for a new class of deep space probes, quantum vacuum probes, designed for a journey of hundreds of millions of light-years into the center of the Boert's void, the nearest and best studied of the great empty regions. The probe would need to travel for thousands of years, powered by advanced propulsion systems. It would need to be completely autonomous, capable of navigating and performing its experiments without guidance from Earth, as the light travel time would make real-time communication impossible. On board, it would carry a miniature laboratory, an array of microscopic Casimir plates, cooled to near absolute zero, capable of measuring forces so small they would make the weight of a single bacterium seem immense. These two predictions, the chiral gravitational waves and the anomalous vacuum energy in voids, became the central focus of experimental physics for the next generation. They were the clear, unambiguous discriminators that would either cement the new paradigm or send it crashing into ruin. Unlike the previous evidence, which was a reinterpretation of existing data, these were forward-looking prophecies. They were falsifiable in the purest sense. The discovery of a non-chiral gravitational wave background would be a fatal blow. The measurement of a normal vacuum energy inside the Boert's void would be equally devastating. The theory had placed itself on the executioner's block, offering two clean, sharp axes for the scientific community to wield. The stage was set for a definitive experimental verdict. The race to build LISA and the first quantum vacuum probes began, a multi-generational effort to answer the deepest question we had ever learned to ask. But even as humanity began this new quest, the implications of what had already been discovered were beginning to ripple outwards, transforming not just our science, but our philosophy, our culture, and our very definition of what it means to be human. Science does not happen in a vacuum. A discovery of this magnitude, the confirmation that our reality is a secondary, emergent structure from a deeper, timeless foundation, cannot remain confined to the laboratories and blackboards of physicists. Sooner or later, its tidal wave must crash upon the shores of human culture, washing away old certainties and reshaping the landscape of our most fundamental beliefs about who we are, where we came from, and what our place is in the grand scheme of existence. The confirmation of the causal substratum, as it began to trickle from the arcane journals of physics into the broader intellectual conversation, did not just change our cosmology. It began to change us. It forced humanity to confront a series of profound and profoundly uncomfortable new truths. The first and most disorienting implication was that time, the most fundamental aspect of our experience, is not real, not in the way we thought. For all of human history, we have lived as subjects of time's relentless, one-way flow. We are born, we age, we die. The past is a fixed memory, the future an unknowable horizon, and the present a fleeting, knife-edge moment that we ride like surfers on an unstoppable wave. Time was the bedrock of our reality, the very grammar of our existence. But crystallizing space-time cosmology reveals this to be a profound illusion. Time is not a fundamental property of existence. It is an emergent property of our particular cosmic structure, a feature of the crystal we inhabit. The arrow of time is not a universal law, it is a local bylaw. It is the rigid, sequential processing of causal information within our frozen reality. But beneath us, in the timeless, liquid ocean of the causal substratum, the past, present, and future do not exist as a sequence. All causal connections, all moments, exist in a state of simultaneous, atemporal potential. Think of it like reading a book. As you read, you experience the story as a linear progression of events, one page after another. You feel the suspense, the passage of time, the journey of the characters. But the book itself, as a physical object, contains the entire story at once. The first page and the last page coexist simultaneously. Your linear experience is a product of the way you are accessing the information, not a fundamental property of the information itself. Our consciousness, trapped within the crystallized structure of space-time, is reading the book of the universe, page by page, but the book already exists in its entirety as a timeless informational structure. This is not a new philosophical idea. The concept of a block universe where past, present, and future are equally real has been debated for centuries, but it was always a philosophical abstraction, a metaphysical speculation. Now, for the first time, it was a direct physical prediction of our best and most tested cosmological model. The evidence for a timeless reality beneath our own was written in the sky, in our particle accelerators, and in the very cells of our bodies. This realization has profound and deeply personal implications for our understanding of consciousness and mortality. If the substratum is fundamentally informational, a realm of pure causal and mathematical relationships, then what is a conscious mind? Then the new paradigm, a mind is not a temporary biological phenomenon, a fleeting ghost in the machine of the brain. A mind is a pattern, a complex, self-referential, self-sustaining pattern of information. In our universe, that pattern is currently being run or executed on the biological hardware of our brains. But the pattern itself, the pure information that constitutes your memories, your personality, your very sense of self, is not necessarily tied to that hardware. The information is real, the pattern is real. And if information is the fundamental currency of existence, as the substratum model suggests, then that pattern may be more fundamental than the physical body that temporarily houses it. This opens a door to a new and radically different way of thinking about death. In the old story, death was the end. The cessation of biological function meant the erasure of the conscious pattern. The information that was you was lost forever. But in the new story, is it? If our space-time is just a crystal embedded in a timeless informational ocean, then what happens when a complex informational pattern like a conscious mind is deleted from the crystal? The model suggests that the information is not destroyed. It cannot be. It is merely released. Death, in this view, may not be an end, but a transition of an informational pattern from one state to another. From being a localized, time-bound process within the space-time crystal to being a delocalized, timeless state within the causal substratum, it is like a complex whirlpool that dissipates from the surface of a river. The form of the whirlpool is gone, but the water molecules that composed it and the energy it contained have simply returned to the river itself. This is not a promise of a traditional afterlife. It does not speak of heaven or hell, or of the persistence of individual personality. The nature of existence as a timeless informational pattern in the substratum would be something so alien to our time-bound consciousness that we lack the language or the concepts to even imagine it, but it replaces the absolute certainty of annihilation with a new and profound possibility. The possibility that consciousness, as a form of ordered information, is a fundamental and conserved quantity in existence, one that can transition between states of reality. It suggests that the universe, at its deepest level, does not forget. The second great paradigm shift was in our understanding of our universe's place in the grand scheme of things. The Big Bang model, for all its grandeur, was a story of ultimate uniqueness. Our universe was everything. It was the only thing. Its beginning was the beginning of existence itself. We lived in the mansion of reality, and there were no other houses on the street. This gave our existence a sense of cosmic importance, of being the sole and singular stage for the drama of existence. The causal substratum hypothesis demolishes this comforting illusion. Our universe is no longer the whole thing. It is merely one possible structure, one crystal that has precipitated from an infinite sea of potential. The substratum, being a realm of pure informational possibility, contains the blueprints for every possible universe, every conceivable set of physical laws. Our universe, with its specific constants and its 3 dimensions of space, is just one of the stable forms that can crystallize. This implies the existence, in a latent, potential state, of countless other universes, a universe where gravity is a repulsive force, a universe with 10 dimensions of space, a universe where the laws of logic themselves are different. All these possibilities coexist as informational patterns within the substratum. Our existence is not a unique miracle. It is one outcome, perhaps one of many, in an eternal, ongoing process of reality formation. We are not living in the only house on the street. We are living in one house in an infinite city, and all the other houses are built to different architectural plans. We can never visit these other houses. They are not parallel universes in the science-fictional sense of being accessible through some portal. They are different crystallizations, different realities with no causal connection to our own, but the knowledge that the potential for them exists, that our reality is just one of many possible answers to the question of existence, is a profound and humbling realization. It resolves the fine-tuning problem in a way that is both elegant and unsettling. Why is our universe so perfectly calibrated for life? The answer is not that it was designed for us, but that we could only have arisen in a universe with a stable, life-permitting structure. U2 du hein, anates dalitis phosesesthas. The substratum may have spawned countless other universes, other crystallization events, whose physical laws were unstable or hostile to complexity. These universes may have existed for a fleeting moment before, melting back into the substratum, their internal logic collapsing under its own inconsistencies. We are, by necessity, living in one of the universes that worked. We are not the chosen ones. We are the survivors of a cosmic process of natural selection that operates on the level of entire realities. This removes humanity from the center of creation in the most profound way imaginable. Our universe itself is no longer special. It is just one stable configuration among an infinity of possibilities. This shift in perspective is as significant as the Copernican revolution, which removed the Earth from the center of the solar system. It is the final step in our cosmic decentering, the realization that not even our entire reality is the center of existence. This new understanding forces us to confront our own contingency. Our existence and the very laws that make it possible are the result of a random fluctuation in a timeless ocean of potential. There is no deeper reason why our universe is the way it is. It just happened to crystallize this way. This is a terrifying thought, but it is also a liberating one. It frees us from the search for a preordained purpose for our universe and places the responsibility for creating meaning squarely on our own shoulders. We are not actors in a play written by the cosmos. We are the authors of our own meaning, within the specific and contingent set of rules that our particular reality provides. The discovery of the causal substratum did not provide us with answers to the ultimate questions of meaning. It told us that we are the ones who must create them. It gave us back the terrifying freedom of a universe that is not for us, but which, through a magnificent accident of crystallization, has allowed us to be. A truth of this magnitude does not just change our books of science and philosophy, it changes our maps, it changes our ambitions. The moment we understood that our universe was not the beginning and end of all things, that a deeper, more fundamental layer of reality lay beneath our own, the future of human exploration was rewritten. The quest for knowledge, the very direction of our species' long-term intellectual journey, was forever altered. The grand challenge for science was no longer simply to understand the laws of our universe. That task, while monumental, now seemed almost parochial. The new, ultimate goal became to understand the causal substratum itself, the timeless, spaceless ocean from which our laws and all other possible laws emerge. This was a shift as profound as the one that occurred when we first realized the stars were not lights on a celestial sphere, but other suns with their own worlds. It opened up a new and infinitely vast continent for exploration, but this continent was not across space, it was beneath it. This demanded a complete re-evaluation of our scientific strategy. For a century, fundamental physics had been driven by the pursuit of higher and higher energies, building ever larger particle colliders to smash matter together with greater violence, hoping to glimpse the unified forces of the Big Bang. But if the Big Bang was a crystallization event, a freezing, then to understand what came before, we did not need more heat. We needed to understand the cold. We needed to understand the structure of the crystal itself and the nature of the liquid from which it formed. This necessitated a new generation of experiments, instruments designed not to shatter reality, but to listen to its deepest vibrations, to probe the delicate boundary between our spacetime and the substratum. The focus of experimental physics began to pivot. While high-energy colliders remained crucial for understanding the properties of our crystal, a new frontier of high-precision measurement opened up. These were experiments designed to search for the subtle, almost infinitesimal ways that the substratum might still be leaking into our reality. Physicists designed experiments to look for microscopic violations of causality in new and exotic particles. They built detectors to search for quantum tunneling events that might be taking shortcuts through the substratum. The goal was to map the interface, to find the thinnest points in the wall between worlds, the places where our reality was most intimately connected to the timeless ocean beneath. This reorientation of scientific priorities was not just an academic exercise, it was a matter of profound and potentially terrifying strategic importance. The discovery of the substratum presented humanity with a spectrum of future possibilities and risks that dwarfed anything we had ever contemplated. The possibilities were almost beyond imagination. If we could learn to interact with the substratum directly, to consciously and deliberately open a gateway to the timeless realm, the technologies that might emerge would seem like magic. Imagine a computer that could solve any solvable problem instantly, by offloading its computation to the timeless parallel processing nature of the substratum. Imagine a communication system that could send information to any point in our universe without any time delay, because the signal would travel not through space, but through the non-local substratum where distance has no meaning. Imagine the ability to manipulate causality itself, to access the informational blueprint of our reality, and perhaps to edit it. These were not fantasies. They were the logical, technological extension of the physics we had just discovered. They were the engineering applications of a timeless reality. But with this unimaginable promise came an equally unimaginable peril. Our universe exists as a stable, crystallized form of reality. It is a delicate, frozen structure. What would happen if we, through ignorance or hubris, were to interfere with that structure? What would happen if we learned how to melt the crystal of space-time, not just in the microscopic inferno of a particle collider, but on a larger scale? The theory was clear: a decrystallization event could, in principle, be triggered. A sufficient concentration of energy or a specific kind of quantum resonance might be enough to shatter the local lattice of spacetime and cause it to dissolve back into the liquid potential of the substratum. Such an event, a localized failure of physical law, would expand outwards at the speed of light, erasing our local region of spacetime. It would be the ultimate, irreversible catastrophe. The very fabric of our reality, the stage upon which our existence unfolds, would simply cease to be. The risk was not merely theoretical. The causal muons were proof that we were already, inadvertently, cracking space-time at microscopic scales. What would happen if we built a collider 1,000 times more powerful? At what point does our scientific curiosity become an existential threat, not just to ourselves, but to our corner of the cosmos? This dual promise and peril created a new and urgent political and ethical debate. For the first time, humanity had to consider the possibility that our technological advancement could, if pursued recklessly, destroy the very laws of physics that make our existence possible. International treaties were proposed, not to limit weapons, but to limit the energy densities of future experiments. A new kind of scientific ethics was born, an ethics that had to weigh the pursuit of ultimate knowledge against the risk of ultimate destruction. Out of this new strategic landscape, a new roadmap for cosmic exploration emerged, a multi-generational plan driven by two great imperatives: to understand the substratum and to do so safely. The first and most immediate goal was the construction of the instruments that could test the two great prophecies of the new cosmology. The Laser Interferometer Space Antenna, LISA, was fast-tracked, its mission to detect the chiral signature of primordial gravitational waves, now seen as the most critical experiment in the history of science. Thlentel of Erna of Pastor Manhave, Permaclusts. It was our only way to read the story of our own creation, to confirm that our universe was indeed born from a crystallization event. The second great project was the launch of the first quantum vacuum probe, an audacious, centuries-long mission to send a robotic laboratory into the heart of the Bowertz void. We had to know if the voids were truly different places, if they were our windows into the uncrystallized substratum. We had to measure the energy of their vacuum, to feel the pressure of the pretemporal ocean. These projects were no longer just about exploration. They were about confirmation, about securing the foundations of our new understanding of reality. This marked the beginning of a new space race, but it was not a race between nations for geopolitical dominance. It was a race for humanity, a race against time, to understand the fundamental nature of our existence before we developed the capacity to accidentally destroy it. It was a race not to conquer other planets, but to reach, before time. The focus of our search for extraterrestrial intelligence also shifted. We were no longer just listening for radio signals from civilizations like our own. We began to search for the technological signatures of civilizations far more advanced, intelligences that might have already learned to interact with the substratum. We began to look for the subtle gravitational effects of their non-local communications, for the neutrino signatures of their substratum-level engineering projects, for the scars or melt zones in spacetime that their activities might leave behind. The search for intelligence became a search for beings who had transcended the limitations of their own spacetime crystals. And so, humanity stood at a crossroads. Behind us lay the shattered fragments of our old, comfortable story of creation. Before us lay a new and terrifying continent of possibility, a timeless reality whose rules we did not yet understand. We had a new map, but it was a map with vast, unexplored territories marked only with the words, "Here be dragons." We had a new destination, the most profound one imaginable, the origin of reality itself. But the journey was fraught with peril, with the risk that in our search for the ultimate truth, we might unmake the very reality that allowed us to ask the question in the first place. The promise was godlike power. The risk was total annihilation. This was the new strategic landscape of the 21st century, a future defined by the discovery that time itself had a beginning, but existence did not. And so, the greatest journey humanity has ever conceived begins. It is a journey not measured in light years, but in a currency we are only just beginning to understand. A journey not to a destination in space, but to a source outside of time. We have turned our most powerful instruments and our sharpest minds toward this new frontier, this boundary between our reality and the timeless, information-rich ocean from which it was born. The stakes, as we have seen, are absolute. The potential reward is a complete understanding of existence and technologies that would make us as gods. The potential risk is the dissolution of everything we are, the melting of our space-time crystal back into the formless potential from which it came. This is the new, terrifying, and magnificent reality we inhabit. Our search for what was there before time did not give us a simple answer. It did not give us a story of a previous universe or a quiet, empty void. It gave us something far stranger. It gave us a mirror. And in that mirror, we saw that our entire cosmos, with its immutable laws and its relentless arrow of time, is an emergent structure, a magnificent accident of crystallization. Our search for the beginning has led us to the stunning conclusion that there may not have been one, not in any way our time-bound minds can truly comprehend. We are not the children of a singular, explosive moment of creation from a true nothingness. We are the inhabitants of a structure of exquisite and terrifying fragility, a four-dimensional crystal of space-time that precipitated 13.8 billion years ago from an eternal and timeless reality of pure potential. The journey we have taken together, from the first detection of a ghostly whisper in the afterglow of creation, has been a detective story written on a cosmic scale. We followed the clues, from the impossible timing of a decaying particle in the heart of an atomic nucleus to the anomalous expansion of the largest empty voids in the heavens. We saw how evidence from the microscopic machinery of life itself, from the quantum dance of photosynthesis, resonated with the geometry of the entire universe, a universe whose fundamental constants appear to be nothing more than the geometric properties of its crystalline lattice. We have seen a paradigm fall and a new one rise from its ashes. We have come to understand our existence through a new and powerful metaphor, that of the crystal and the ocean. We live within the crystal. We are patterns within its rigid, ordered lattice. Our lives, our thoughts, our very perception of reality are governed by the rules of this crystal, the laws of physics. The most powerful of these rules, the one that defines our every experience, is the arrow of time. It is the sequential, cause and effect structure of the crystal, the way information propagates, one moment at a time, through its rigid form. But we now know that this crystal is not all there is. It is an island, a magnificent and vast island, but an island nonetheless, floating in an infinite, timeless ocean. The causal substratum, a realm of liquid potential, where all possibilities, all laws, all histories coexist in a state of atemporal grace. Our universe is one of the possibilities that became actual. One of the songs that was chosen from an infinite silence. This recasts our entire existence. We are not merely fleeting biological accidents in a cold, indifferent, and fundamentally empty universe. That was the old story, a story of magnificent loneliness. The new story is stranger, and perhaps more hopeful. We are expressions of a timeless, information-rich reality that has, within one of its myriad possible forms, achieved self-awareness. We are the crystal learning to think. We are the substratum through the intricate and improbable machinery of biology and consciousness coming to know itself. Every life, every thought, every discovery, every work of art is a complex and beautiful pattern that has formed within this cosmic crystal, a pattern that reflects, in its finite and temporary way, the infinite potential of the substratum from which it ultimately arose. Our existence is not diminished by this discovery, it is imbued with a new and deeper significance. We are not just matter and energy, we are information. We are patterns, and a pattern, we have learned, may be the one thing in existence that can truly approach immortality. Our perception of a linear journey from a fixed past to an open future may be the grandest illusion of all. It is a powerful illusion, a necessary one, for it is the framework that allows for experience, for growth, for love, for loss. The story of our lives is a story that requires a sequence. But the discovery of the substratum suggests that this story, our story, is written in a book that already contains its ending. We are merely turning the pages. This does not mean our choices are meaningless. It may mean something far more profound. It may mean that our choices, our acts of free will, are the very mechanism by which the universe selects which page to turn next, which of the infinite potential paths becomes the single, actualized story. We are not just reading the book, we are writing it, even as we read. We are the co-authors of the crystal's unfolding pattern, participants in the ongoing act of creation. The journey forward, the next great chapter for our species, is therefore no longer about looking back to a single moment of creation. We have seen that the question of a beginning was a red herring, a limitation of our time-bound language. The real journey is about looking deeper into the nature of existence itself. We now know, with a certainty that borders on the terrifying, that another layer of reality lies just beneath our own, a reality that operates on a completely different set of principles. The next great frontier for humanity is not across the vast distances of space, but across the infinitesimal boundary of time itself. It is the quest to understand, and perhaps one day, to touch, the timeless ocean that lies beyond our crystalline shore. This is a journey that will require a new kind of explorer, a new kind of courage. It is a journey into the very grammar of reality, a quest that will force us to question the meaning of I, of now, of is. This discovery does not make our lives, our struggles, our triumphs any less real. The fact that the play is written on a static page does not diminish the drama we feel as we experience it, line by line. The fact that our reality is an emergent structure does not make it any less our home. In many ways, it makes it more precious. We are the inhabitants of an extraordinary and perhaps rare structure, a configuration of reality that allows for the miracle of conscious experience, for the universe to hold a mirror up to itself and be struck with awe. Our purpose, if we are to have one, may be simply this: to be the patterns that appreciate the crystal, to be the part of the universe that can comprehend, however dimly, the magnificence of the whole. Our science becomes a form of reverence, our art a form of worship, our lives a fleeting but profound act of cosmic self-awareness. And so we are left with a final and resonant question. A question that will define the future of our species and perhaps the future of our reality itself. Now that we know this deeper, timeless reality exists, what is our responsibility to it? And what will we become when we, or our descendants, finally learn to cross that boundary? Will we be humble explorers, dipping our toes in the timeless ocean with reverence and caution, content to learn its secrets without trying to master them? Or will we, in our insatiable hunger for knowledge and power, attempt to become the masters of the substratum itself, to learn how to melt and reform the crystal of space-time to our own design? The choice ultimately will be ours. It is the greatest test that consciousness has ever faced, a test that will determine whether our pattern is one of wisdom or one of self-destructive pride. The universe is watching. The substratum is waiting. The story is not over, the book is still being written, and the pen is in our hands.